Mm.
Hello.
अभी मैं
ये
लिखी हूँ ना, ऐसा काम होता है इसलिए मैं लिख रहा हूँ, सोलो कितना है इस तरह से। तुम लोगों से सबसे टाइप ऑफ, अरे मैं उसका माइक ऑन है तो मैं वही बोल रहा था।
A very warm and pleasant morning to one and all. One of the very famous quote by Nick Bostrom states, nanotechnology has been moving a little faster than I expected. Virtual reality a little slower. With this quote, myself, Poonam Bajoria, welcome you all to the flagship event of IEEE called Student Research Symposium 2024. This event is co-organized by IEEE Madhya Pradesh Section Electron Devices Society Chapter, IEEE Nanotechnology Council Student Chapter in IIT Indore, and IEEE Sensors Council's Chapter, IIT Indore. Here we aim to inspire and encourage the undergraduate and postgraduate student community throughout the globe to pursue their career in research. The main objective of SRS'24 is to expose budding minds to esteemed researchers and industry experts, providing them with an interactive platform to engage with research scholars. The symposium will feature various events including thesis presentation, model presentation, oral presentation, and one-slide presentation, all designed to foster healthy competition and facilitate the presentation of research work. So, this is the outline of our first day of today's session. We have plenary talk session followed by oral presentation as well as one slide presentation. Moving on to our plenary talk session, I would like to invite Professor Nausheen Nasiri, Associate Professor, School of Engineering, Macquarie University, Australia. Professor Nausheen Nasiri is the head of the Nanotech Laboratory at the School of Engineering. She is one of Australia's 2021-2022 Superstars of STEM 40 under 40 most influential Asian Australians and the recipient of 2023 Cancer Institute NSW Fellowship, 2022 L'Oreal UNESCO for Women in Science Fellowship, Royal Society of New South Wales Warren Prize in 2021 and NSW Young Tall Poppy Science Award in 2019. Her research is focused on design and fabrication of nanostructured material, miniaturized sensor technologies, and wearable electronics for personalized and preventive medicine. She serves on the editorial board of nanotechnology and nanomanufacturing journals. Her vision is to combine state-of-the-art techniques in the field of nanomaterials, nanoelectronics, and chemistry to develop innovative nanomaterials that can potentially transform the landscape of nanosensing technologies. She is a passionate science communicator who has received considerable outstanding recognition for her research, including TEDx Sydney Salon 2017, TEDx Macquarie University 2019, and TEDx Bleas Street 2020. You can please begin with the talk. Please.
Thank you so much. Thank you for the very kind introduction. So I'm going to share my screen. Okay. Just to double check, you can see my screen?
Yes, ma'am. It's visible.
Okay, thank you so much. So thanks for having me. It's my great honor to be here. So today I'm going to talk to you about highly porous nanostructured materials, which in my team, we are using them mostly for advanced nanosensing technologies. In order to give you a better idea about what my team is doing, so we are actually a team of a diverse team of people with different expertise. We have students who are chemists, students who are physicists, materials engineers, they are mechanical engineers. I have students who are from medical schools, like they do tissue engineering, students who came from pharmacy, and also textile engineering. So it's a wide range of expertise that we have. But what we do have one goal to use state-of-the-art nanofabrication techniques to create new structures, to create new nanomaterials, nanofilms, nanoparticles, and then mostly use them for nanosensing application. But I want to also acknowledge that not everyone in my team is doing nanosensing. We have students who are doing other type of application. And apologies if it's a bit crowded. So outside they are refurbishing the corridor here, so it's a kind of there is a loud noises if you can hear it on the background. But so in my we do a lot of nanoparticles. So we grow films, as you can see here. We make different types of films. Most of them are porous materials. We have flame spread pyrolysis technique, which is one of the method we use. If you see, this is the fire spraying. We have a liquid being combusted inside the fire, and then particles generated. They go up, and then we put our substrate here, and you see this one, and then we have all these particles going up, sitting on the substrate, and then we create this fluffy nanostructure on the surface. We can make it super porous, which is a good thing if you want to use them as a sensor. We also have plasma enhanced chemical vapor deposition, and then we grow nanowires, we grow thin films. We also have techniques to like electrospinning to make different type of nanofibers, mostly polymeric fibers. And sometimes we combine them, like we make the polymeric fibers and then we coat them with nanoparticles. And sometimes by changing the nozzle, we actually create different type of nanofibers. This is particularly useful for drug delivery if you're interested in that area. But yeah, it's in our team, we usually care about different type of structures and materials, and then we collaborate with other people which use them for a wide range of application. But let's talk about sensing application, which I think is more relevant to the audience of this event today. We make different type of sensors. Like, as you can see, they're mostly very tiny sensors. We can go smaller than this. We usually don't do that because it makes the research a bit more difficult, but whether it is possible to go even smaller or not, yes, it is possible. But usually we have a substrate. It can be ceramic, it can be glass. Then we have electrodes on the substrate, and then we grow different type of structure on the substrate. So in our team, the expertise is the structure, not the substrate. We usually buy the substrate, but then we grow different type of material and different like we grow this type of structures, which is made of tiny particles, like 10 nanometer or 7 nanometer particles being stuck on the top of each other and create this fluffy structure. Or we create this type of like a volcano shaped structure, like an island on the surface. We even make them on a flexible substrate, and then we make them on ceramic. So it really depends on the application, what type of materials you want. So then we choose the right substrate, right electrodes, and then we grow different type of film on the top of that. In general, we do use these materials in a wide range of application, use them as photodetectors, as gas sensors, which today I'm going to focus on these two. But we also use them as pressure sensors, for example. We use them for catalysis application. As I said, I have people who use these films for tissue engineering. I have dentists in my team who use them for like a membrane that can separate tissue from bone. And then we also use them for like functional coating, like make them as the hydrophobic surface, which can repel the water, or hydrophilic surface, which can absorb the water. But because of the time today, I'm going to only focus on these two applications, which is mostly light sensing and gas sensing. Why I was interested, like I came to Australia like 12 years ago when I started my PhD, and back then I decided to do my PhD on UV sensors. The reason is that here in Australia, there is no UV off season. Like if you look at the Australian map, even in September, which is kind of is a cold weather here, more than half of the country is exposed to either very high or extreme level of UV. And then if you look at the October or even November, look at the November, the entire country is under very high and extreme level of UV exposure. In Australia, people get skin cancer. Like, I mean, skin cancer is one of the problem. I mean, you get sunburn, you get premature aging, you get eye disease because of the extreme level of UV. But of course, the main problem is skin cancer. In Australia, every 5 hours, we have one Australian dying from skin cancer. And then 2 in 3 Australians will be diagnosed by skin cancer by the age of 70. That's why in this country, we call it national cancer, because more than 70% of the population will get skin cancer by the time they get to the age of 70. And then if you look at this graph here, we are number one in the world in terms of the incident rate of skin cancer, which is the main problem here. So when I came to Australia 2 years ago, I decided to work on a device that can accurately measure how much UV is absorbed by our skin. So it's a kind of a light sensor, because based on the statistics, this high number of the incident, 94% of the skin cancer in Australia is just because of overexposure to UV. So it's not like a genetic problem. It is just because the ozone layer here is so thin, and then there's a beautiful country, it's a landscape, there's a lot of like a ocean, and then people want to spend time outside and they get exposed to high level of UV. And then UV, you don't see UV, you don't feel UV. So they cannot actually estimate how much or how long they've been exposed to what level of UV. And that's why their skin become damaged. The DNA of the skin changes over time. And then years later, when they get older, they develop that abnormality, that change in the skin, they develop skin cancer. Okay, let's learn a little bit more about UV. There are some misunderstanding about UV, which I think create more problems in public. The first one is that if you're swimming in ocean, down to 150 meters into the water, you still get exposed to UV. So do not assume that if you are swimming and your body is covered by the water, then you're going to be safe. It's not the case. UV can still penetrate into the water, and then you get exposed to UV, and then you still get damaged. Even if it's a rainy day, you still get exposed to 25% of UV. Of course, if it's a cloudy day or it's a light cloud, the exposure is higher. And then majority of the UV, of course, it is a direct exposure, that if there's a sunlight directly into your skin. But in many cases, even if you are standing under the shade, like you found a shade, a building or a tree, and you're standing there, and you assume that now you're safe, you're wrong, because UV will hit the ground and will be reflected into your face. And it really depends on an environment. Like if it's the snow, up to 90% of the UV will be reflected from the snow directly into your skin. But of course, if you are in somewhere which has a grass, then you might be in a safer environment. But yeah, just don't be fooled that if you are on the shade, then it means that you are safe from UV exposure. And that's why people started developing different type of wearable technologies for UV radiation to regulate, or to at least to kind of measure the intensity of the UV which they've been exposed to. Here are some of the examples. This group of sensors, they're called colorimetric sensors, which means the color of the sensor change based on the exposure to UV, which is pretty simple. So you actually have a particle or a material which is sensitive to UV, and then you use dye as a color, and then you print it on a polymer. Then the particle will absorb the UV, react, and then the dye color changes, and then you see it as a different color, like it actually appears or it faded over time. But the problem is that they are disposable. Like once the color change, it is not reversible. So you have to check it out, and then you have to use another sensor, which can be problematic. So I want to talk about two projects that has been done, not in my team, but here in Australia. So one is done by a team in UNSW, which is University of New South Wales in Sydney. So they actually did a clever thing. They removed the cartridge, the ink from a normal printer, like a $20 printer. They remove the ink. They fill it with the polymer PVP, and they also fill it with the a dye, and they also have a titanium dioxide, which is quite sensitive to UV. And they printed this piece of papers, and then as you see, the more, and it was blue beginning, the color was blue, and then the more exposed to UV, the color faded over time. And then the criticism to this team was that it is not inclusive enough, like, because then the level of UV and the safe level of UV depends on your skin type. So if you print it like this, then does it work for every different type of skin type or not? So then there was another team 2 years later in RMIT, which is also a university in Melbourne. They come up with regulating the amount of dye used in this sensor, and then they printed for different skins, and they also printed different catalogs. So you can buy you can use different catalog based on your skin type, and then you can actually see how much is exposed, and then based on that, like the end user can actually use this. But the main problem that I had to both of these research is that once the color change, first of all, once the color change, you have to check it out, and they're not really environmentally friendly, and then you have to use another one. The other problem is that sometimes you use this pad on your, let's say on your shoulder, around your wrist, and you don't pay attention, and suddenly when you look at that, the color change already, and you don't really know when the color changed half an hour ago or 3 hours ago. So there is no communication with the end user and the sensor to give you a warning that, hey, you reached to the kind of a safe limit of the exposure, so you better seek shade. That's why and then, okay, so it's not only Australia, there's also a lot of different universities all around the world, even companies, L'Oreal, all around the world. There's also people who actually tattooed this ink and the particles under the skin, and then you see the tattoo once there is no UV, and then you go outside and the more UV absorb, the tattoo disappear. So there are a lot of innovative, crazy things that is happening all around the world, but all of them is based on changing the color. And to me, that was a problem. So I actually wanted to work on a device that is kind of an electronic device. So it gives me a signal when there is UV, and then when I go back indoors, then the signal is off. So not only it is reusable on and off, on and off, on and off, but also I can actually program it in the way that once it reaches to a limit, it will send me a text message, for example, or it will give me a warning. It will give me some level of notification. So I can moderate, I can regulate the amount of like the time that I've been exposed to a dangerous level of UV. So then the best way of doing that is to use semiconductors. And in semiconductors, I mean, I'm pretty sure that everyone is aware of the concept of the semiconductor, but very, very quickly. So we have metals, which there is no gap between the conduction band and the valence band. So they're always conductive. So they are useless if you want to use them as a sensor. Then we have insulators, which there is a very huge gap between the conduction band and insulator and the valence band. So then again, they are useless as a sensor because they're never conductive. And then we have semiconductors, which they have a band gap. So as long as you have enough energy to excite this electron to jump from valence band to the conduction band, you get a signal. And once the energy is not there, then the electron will go back to the valence band, and then you lose your signal. So then, based on the energy, you can actually use it as a sensor. So you can actually excite that electron by heating, as you can see a simple experiment here. So this is a semiconductor. It's not a conductor, so it's a semiconductor, so the LED is off. But then once you heat it, you have these electrons jump from the valence band to conduction band, and the LED is on. But at the same time, you can also use it as a photon. So you don't need to heat it, but the photon from UV can be used as a source of energy, excite the electron, jump from valence band to the conduction band, and then you get this signal. So if I have my LED on, off, on, off, on, off, then I should be able to get the signal and then recovery, response, recovery. So that is the concept of how these UV sensors work. In terms of materials, you need to find a material which has the right band gap, because you only want to get the signal from the UV. You don't want to get the signal from the visible spectrum, because the visible spectrum is not dangerous for our skin, but the UV spectrum from the sun radiation is dangerous for our skin. And zinc oxide is one of the very good materials which has the right band gap, is exactly within the UV range. So there is no signal from the visible radiation, and once you pass the visible and you get into the UV, you can excite the electron in the zinc oxide to jump from valence band to the conduction band. And that's why zinc oxide has been used also in sunscreen, for example, to protect our skin from UV radiation. So today I want to talk to you about the journey we took from like 10 years ago to develop sun watch, which this is the name we chose for this device. It's a smart UV nanosensing watch. And currently, the project is funded by Cancer Institute in New South Wales in Australia. But I want to walk you through the journey. So, as I said, we use this technique. It's a flame spray pyrolysis. It's quite simple, but very unique. If you want to make metal oxide, flame spray pyrolysis is one of the most efficient techniques to create metal oxide for you. So if you want to make metal oxide, all you need is a liquid precursor, and then there is a syringe here. I mean, there's a needle here going through this, and then you use the liquid precursor, you purge it by a pump through this needle. There is a high pressure of oxygen. So once the liquid is coming out of the needle, the oxygen is just shooting the liquid and atomize it into tiny, tiny droplets. So these tiny droplets here, they are nanoliters of the droplets, which has a metal atom inside. Let's say you want to make zinc oxide. In your liquid, you have a flammable liquid, which is all solvent, and then you have zinc atoms. You dissolve it, you purge it, the liquid comes out of the needle, oxygen hit the tiny liquid, atomize it into nanoliters of the droplets, and then in that fire that you see here, that tiny droplets burns away. All stays there is the metal atom, which is zinc, and a lot of oxygen. So then combustion happen, and then every single metal atom will be oxidized into metal oxide. So you end up with a lot of billions of zinc oxide nanoparticles. They go up. You have a substrate holder. It's a substrate holder, which is water cooled. And you put your substrate, which is your sensor substrate. You put it here. Particles generated go up, and they sit on a substrate. If you look at this substrate after you kind of spray it, you look at it from top, it's going to look like this. And then if you look at it from the side, this is your substrate, and this is your film from the side. So we can make any type of metal oxide. If I have titanium in my liquid, I will end up with titanium dioxide. If I have tin, I end up with tin oxide. I have zinc, I end up with zinc oxide. But you cannot make anything else. You can only make metal oxide, because whatever you spray is going to be oxidized. But it's working very well for us. We made zinc oxide, and then we use them for UV sensors. In terms of UV sensors, this porous structure, which I have it on the left, is kind of compared to a dense structure which is made by another technique, any other technique. And then we show that in this situation, the porous structure works very well as a UV sensor. If you want to make a good UV sensor, you need two things. Firstly, you need to have a very, very low signal if there is no UV, which we call it dark current. Dark current, not necessarily in darkness, it means that there is no UV. When there is no UV, you wanted your sensor to give zero signal. The signal is current. And then when there is UV, you want your sensor to give a very high current. So you want the difference between these to be as big as possible. In order to do that, so how the system works? The system works based on the absorption and desorption of oxygen. So in the normal environment, like if I make my sensor and I leave it in this room, oxygen sits on the surface, capture the extra electron which is in my zinc oxide, which is an N-type semiconductor, and then won't let that electron to move around. In that case, I will end up with a very low dark current because there is no free electrons to move around. And then when I have my UV illumination, I'm generating extra electron pairs, and then that oxygen is desorbed from the surface. So I have electrons going through my film. So I actually end up with a very high photocurrent. And that's why my sensor as a porous structure works way better than a dense structure. But I'm going to focus from now on the work that has been done in the past 2 years in my team, because I don't want to walk you through the 12 years of journey. Some of the work is from like 10 years ago, 8 years ago. I want to only focus on the recent advancement. So the first work is done by Jaden, who's currently a postdoc in my team, but back then he was my PhD student. So what Jaden did, again, this is the same technique, spraying particles sitting on a substrate, and they grow, these clusters grow. And then if you look at it under the microscope, they look like this. This is your film, and this is your substrate. But what Jaden did, he actually added a tiny liquid of ethanol. He dropped the liquid of ethanol on the side of the sensor, and he let the ethanol to be absorbed by the sensor. The images you see at the bottom is in macroscopic images take under a microscope when he dropped the liquid. So he put this droplet, he let the liquid goes into the sensor, and then he let it dry. And it's ethanol, and it dries so quickly. Based on all the parameters, which I'm not going to bore you with that, he changed the structure into this unique structure here. What I'm going to show you this video, which is taken under the microscope while we were putting the droplets, okay? So this is where you look at it under the microscope. That is a droplet coming. So the film is zinc oxide. The droplet is coming, and it's only 5 microliter of the droplet. So you can actually barely see the droplet is so small, but we're talking about such a tiny scale. And now the droplet is evaporating. While it is evaporating, it will pull the film into different direction. And then you look at it from side view. So we actually created these clusters on the surface. So while it is evaporating, it's all based on the capillary force, and it's all based on the Laplace pressure. But at the very, very end, I'm going to show you at the very, so this is the film before we put the droplet. This is top view. This is the tilted view from side. And this is where the film after we put the droplet. Why we do this? Because this structure has been proven that it gives us an extremely higher signal. Look at that. So this is the structure we put before we put the droplet. That is the signal we get from the zinc. And this is the structure after so we did nothing. Like the difference between these two structures is actually 2 minutes. You have the sensor, you test it, we put the droplet, we let it dry, and then we test it again. However, I have to tell you that we tried different droplets. We tried different way of doing that. We even tried different original structure. It is not just you put a droplet on any sensor and then so if you want to know more about it, you just feel free to go and read the paper. But what I wanted to emphasize is that in my team, we are focused on creating new nanostructures based on the application. Like if you want to make the application, the sensor works better in this environment, then we can change the structure in the way that is going to be more signal and also faster signal. You can see that this one is so slow in terms of how slow it responds to UV, but then you can see how significantly it became faster. I'm going to skip this one. And then you can actually see how stable it is. Like we've tested it like 1,000 times. Every time on, off, on, off, on, off, it actually goes back to the same level, which is very important. But in majority of the research done in the laboratories, when you test the sensor like 20 times, the sensor performance drop. But in this new structure that we developed, it's actually very stable. But the structure is not the end of the story. We actually, after this, we thought about what if we make a composite out of it. As I told you, with this technique, we can only make metal oxide, but we always wanted to make hybrid materials, composite materials, but we couldn't because I cannot make carbon nanotube, for example, by this technique. But then what we did is that in that droplet of ethanol that we drop it there and spread it through the entire film, we added carbon nanotube into the droplet. And now the droplet going into the structure not only changed the structure from this to this, but also spreading carbon nanotube into the structure. You can literally add anything you want into that droplet and then not only change the structure, but also change the composition. Why we added carbon nanotube? Because we wanted to get a better connection between one cluster to another cluster. As you can see here, these clusters somehow separated from each other. And we didn't like that. We wanted to make sure that all these clusters are communicating with each other at the same time, that they're communicating within the cluster. So as you can see here, this is a carbon nanotube. So if you imagine that this is one cluster and this is another cluster, so not only each cluster is connected to the electrode, but also this cluster through carbon nanotube, which is a conductive material, is also connected to another cluster. And this is the macroscopic image. This is a carbon nanotube, and this is the zinc oxide nanoparticles, which are not only connected to each other, but also connected to the carbon nanotube. And in these SCM images, you can also see that these are carbon nanotube connecting one cluster to another cluster. And of course, adding carbon nanotube again make the sensor respond even better than just changing the structure, okay? And then the paper was accepted in this journal, but also the art, the design, the graphic was also accepted on the front page of the journal. As you can see, these are different clusters. On the top of the electrodes, these are the droplets left from the ethanol. And then as you can see, all these clusters are communicating with each other. And that's a droplet which is dropped from here and then going through the entire film. And all these clusters are actually communicating with each other using this carbon nanotube. My other student, it is not published yet, but my other student used polymer. So within that droplet, we now wanted to see whether we can add polymer. And in this time, it is a conductive polymer. It's a P.PSS, which is a very conductive polymer. So we dissolve it into a liquid. In this case, is methanol, because every time you need to make sure that the liquid is the right liquid for dissolving your reinforcement material. And then as you can see, not only we made this cluster, as I said, but I want you to have a look at that. This cluster is connected by a tiny bridge of a conductive polymer to another cluster, and this cluster is connected to another one, and this one connected to another one, and this one. So the entire film, each cluster, not only from the top, but also all the way to the bottom, is connected. But again, it is not just random. We try different polymer, we try different liquid, we even try different concentration, because if you use too much of the polymer, then your entire cluster will be covered by polymer. And you don't want that. You want the clusters to be zinc oxide because they are doing the UV photo detection. But you want the clusters to be connected with each other. So then the polymer will do the connection. If you use too much of the polymer, the zinc oxide will be covered by polymer. Then you don't do that UV photo detection that you wanted. And then if we take too many photos, look at that. This is another area. Again, this cluster communicated with this one, communicated with this one, communicated with this one. So the entire film were somehow connected one cluster to another cluster using this very thin layer of polymer. So again, now I want to talk about very recent papers that we publish in small. So let's go back to the flames pyrolysis. Again, the same technique. We make a lot of nanoparticles, as you see in this photo, and they're sitting on a surface on the top of each other. One of the problems in this case is that if you are dealing with billions of nanoparticles, the communication between one particle to the another particle is very important. If these two particles are not communicating properly, the electron inside one particle cannot move to another particle. So then over time, this electron will recombine with the hole, and then you will lose that. So you won't get the signal. So what you want this particle to communicate with this one, to communicate with this one. So you want all these billions of particles to perfectly communicate with each other. One way of doing that is that once you make the sensor by flames pyrolysis, you put it in the oven and you heat it at the right temperature. It depends on what material you have for the right time. Why you do that? Because you want to create a tiny channel between these two particles on the interface, so then the electron can pass through. Because if there is no channel, the grain boundary, the boundary between the particles, they work as a wall, they work as a barrier. So the particle hit the wall and then stopped here, cannot move to another one, okay? Usually we put them in the oven. The problem is that if you put them in the oven, usually it is like 300 degrees, like 10 hours. There is no way that we can make flexible sensor on a polymer substrate because no polymer can handle 300 degrees. So until now, we could never make a flexible UV photodetector. It was always a UV sensor which is made on a glass substrate or a ceramic substrate. But Jeff, my master's student, what he did, Instead of putting it in the oven, he actually put the sensor inside a Petri dish. I'm going to show you a video, but he put them inside the Petri dish, and then he filled the Petri dish with a vapor molecule of acid, acetic acid in this case. So then what happens inside the Petri dish is full of acid vapors, and acid vapors, they sit at the interface between these two particles, and they tiny dissolve the interface. And then once you remove the sensor from the Petri dish, everything evaporates, and because it is dissolved in this area, the atoms in this area start moving, so you kind of create that connection without putting it in the oven. I'm going to show you this video. In this video, what you see, this is a substrate, is a glass. The black dot you see here is just a tape. We just tape the glass, and you're seeing it from the top. So it's just a Petri dish, it's a glass, and the foggy white area here is just a zinc oxide. It's a zinc oxide film on a glass. So he crossed these 3 points here. This is where he is putting 3 droplets of 1 microliter of acetic acid, which is a very low concentration of acetic acid, only 1 mole. He put them here and he closed the lid. It's just a normal glass Petri dish. And this is a time-lapse video of 15 minutes of what acid vapor does to the particles within only 15 minutes. So what I want you to look at that is just look at the transparency of the film. Look how the transparency changes over time. As you see from the edges, it starts from the edges, and now it is less and less transparent because the particles are merging. So then the film is shrinking a little bit. And then once you get to the very end, look how it is significantly changed the transparency, which means that the particles are now connected with each other. So if I show you the very beginning, and then I go very fast, look how transparent it is here, and then look how the transparency changed within only 15 minutes. So doing this, we didn't even need to put the sensor in the oven, and we didn't even need to heat it up to 300 degrees, and we didn't even need to wait for like 10 hours. We could actually make this connection between the particles within 15 minutes at room temperature. So once we've done this, at the same time, there is another team, there's another group of students in my team which have an electronic background. They try to take the sensor out of the laboratory and test it outside, because all these are more of the science project, but then we also wanted to do some of the electronic project as well. So initially what we did, we tested it in the lab. We have an LED, we put the sensors here, we have a picoammeter, we changed the intensity of the LED, and we measured the sensor signal by the picoammeter. But then the first time students took it outside on the campus, they created a tiny, like using Arduino Nano, they created a tiny board, and then they tried to see whether the sensor works in a real environment or not. And then in 2020, for the first time, we tried to make a wearable technology out of it. So we kind of, I think I have it here. Yes, so we kind of put things together, everything off the shelf, we put them together, and then we 3D printed the case, and then we develop an app. So then the sensor, this is a sensor. The sensor is receiving the signal. It tells you what is the UV index. We program it already. And then we also talk to you as a, like where sun is, or 6 shade, or wear hat. And then also at the bottom, you can collect the data. You can even go back and see what was how much you've been exposed to what level of UV. This is the first wearable technology we made. I mean, back then, to us, it was very beautiful. But as you can see, it's quite bulky. So after that, we started advancing our expertise into what if we design our own PCB. So then the students learn how to design the PCB. So this is a sensor. The UV sensor is sitting here. On the sensor, we also have temperature and humidity sensor already embedded. So as you can see, that is the UV torch. We calibrated the sensor based on the level of temperature and humidity, because we realized the sensor signal changed a little bit. But as you can see, my student is holding the torch closer to the sensor, and then you can see the signal changes, and then it goes further, and then the signal. So this is now 0, and then when it's holding it closer, the UV index change, and you see it at the bottom as well. And since then, we hired different type of students with different expertise. We expanded our expertise into what if we kind of design a variable PCB, like everything is going to be variable. What if we go with the variable sensor, like a flexible sensor as well, flexible PCB. We even made these ones, which we put them on the, I think I should have it somewhere in my office. We also changed the sensor into something that instead of communicating frequently with the app, because that eats a lot of battery, we put an LED in the sensor that the color of the LED changes based on the level of UV. Like if the level of UV is safe, the LED will blink green. If it's a bit higher, will blink orange. If it's much higher, red. If it's extremely high, it will blink purple. And then at the top of that, we designed a tiny space for the SD card, so the sensor's data will be recorded on the SD card. This way, we can save a lot of battery, so the device could operate for days. But then if you wanted to communicate it frequently, that will eat a lot of battery. So that is the UV sensors. I'm going to very quickly touch base on, now that we got to this point, we thought that what if we use it for other sensing applications as well? So like UV sensing, light sensing is one application, but what if we use it for gas sensing application? Because as I said, the sensor is very, very porous. So if it's porous, then it should have a lot of surface area. And then we should be able to detect gases. We should be able to detect tiny concentration of gases. So we use them for a wide range of gas sensing application. Here are just some examples. As you can see, we can even detect like sub ppb, which is parts per billion of gases at considerably lower temperature. It's not room temperature, but 150 degree. It is considerably lower temperature. And then by changing the structure, by changing the composition, we could make it sensitive to some gases and make it not sensitive to other gases, for example. In this project, as the gas sensing, which the device, we call it nanoelectronic nose. We're working with some companies here in Australia. So there are some companies that they are funding our research. One of the companies, the company named Accent, they are interested in detecting whether cows are pregnant or not. The company already has a device and they capture cow's breath in these bags. They take it to the laboratory, they run experiment on the sample, on the breast sample, and they realize that there are some biomarkers in the animal's breath which can tell you if the animal is pregnant or not. And it can tell you early, and it can tell you in a non-invasive way. So they become interested in developing tiny sensors, embed them into the device, so then they don't need to take the sample and then take it to the laboratory. They can actually do the analysis in situ on the farm. So we've been working with them for like 2 or 3 years now. There's another company, they're interested to know the gases produced by bees inside the hive, because apparently bees get stressed and they release different gases. When they are overcrowded inside the hive, they release gases. When the queen bee is dead, they release different gases. And this company is interested to know, to monitor them, remotely monitor to know what is really happening inside their beehive. So they're interested in developing different gas sensors that can detect all these changes inside the hive. Just very quickly, we also work on pressure sensor. As I said, as I've told you, pressure sensors that can be used for like a stretchable, pressure, flexible sensors. We're working with people in hospital at Macquarie University. They want to know the pressure when they have the prosthetic shoulder. They want to know the pressure between the joint. So my student is developing pressure sensor to see if we can map the shear and also the tension between the two joints as well. And as I said, we use them for hydrophobic and hydrophilic surfaces. Not all the applications are sensors. So for hydrophobic surfaces, it can repel water. This is just water, it's just colored. This is a coin which is not coated, and this is Australian coin which is coated by manganese oxide, coated by titanium dioxide. And then once you put it in the water, it's hydrophobic, it hates water, so it actually repels water. It repels it up to 0.5 centimeter. What is the application? It has a lot of application. First, you can use them as a self-cleaning surfaces. Let's say you have dirt on the surface. And then if the surface is hydrophobic, then it means water will beats up on the surface. It's not going to spread, but it will beats up and it rolls off. So then if you have a dirt like this video, the water, while it is rolling off the surface, it can collect the dirt and then it can remove it. The purpose is for solar panels. Right now, Australian government, they just give you free solar panels if you want to install on your roof. But one of the problems is that they get dirty. And then people have to go there and then wash them. Doing it on a household scale is doable, but think about the solar farms, that is kilometers of solar panels. Who's going to wash them? Because every time they get dirty, the efficiency drops significantly. But if you have the solar panels being coated by a very thin hydrophobic layer, then once it is raining, or even a drone which can go up and then just spray water, the water can beat up and then clean the dirt from the surface, so you can actually do a better cleaning condition. And I think this is my last slide. Yes. So lastly, it also has application in construction. This one is not the video from my team. It's just I just found it on the internet. But this area, it is coated by hydrophobic layer. And this is a cement, and this one is not coated. You can see that if it's raining, for example, the water can penetrate into the cement, but it cannot penetrate if it is hydrophobic. It beads up. And that will give the cement a longer lifetime. Look at that. It will go here, but then in this case, it will stays there, which means that it is not permeable, which means that it's going to last longer. What is the use? The use is that it can be used, like if you have metal pieces inside the concrete, this one will be corroded. But then if the concrete is hydrophobic, then the metal piece stays there. So it can be used as anti-corrosion coating. Another application is that if water cannot penetrate into your cement, then it means that in a cold environment, it will not be frozen. So it can be used as anti-icing. As you can see, there is no way that the water stays there. So there is no way that there is an ice created on the surface. So there's a lot of application. You can also create hydrophilic surfaces, which when the water sits there, it doesn't beats up, but it spreads. If the water spreads, then it means that there is no fog, because fog means that the tiny vapor droplet sits on the surface and beats up. But if they sit on the surface and spreads, then you can actually, like all the mirrors that we have in a shower, and they get foggy. If you spray hydrophilic layer on the surface, then it's not, you're going to create an anti-fogging. It can be also used for reading glasses. It can be also used for the goggles that people use when they go skiing, so it can clear the vision. But of course, I give you the talk, but all this work has been done by the research team in the laboratory. I'm so grateful of this wonderful, hardworking, brilliant mind. And as you can see, we have people from a very different background, from people who do organic materials, who do pressure sensors, tissue engineering, photodetectors, and also gas sensors and electrochemical sensors. So it's a very, very diverse team of researchers in the lab. Thank you so much.
Thank you, Professor Noshin, for such an informative session. Now the floor is open for question answer. I would request the participants to please switch on their audio as well as video and ask their queries by introducing themselves.
Hello, ma'am. Hello, ma'am.
Hello.
Yeah, ma'am, I'm Shorjit Mukherjee. I'm pursuing MS research at IIT Indore. Ma'am, I have one question. Like, your group is also working on gas sensing technology. So, is the fabrication method same for the UV photo detectors that you have used at EPOH for after synthesis of the structure? So, is it same for this gas sensing?
Yeah, I mean, we use similar, generally it is similar, but the one I've told you about, the UV photodetectors, it is specifically ethanol on zinc oxide. So we realize ethanol is the best liquid we can use for zinc oxide. But for gas sensing, it really depends on what material you use as a gas sensor. Like if you use zinc oxide, then yes, ethanol still could be the best one. But then some of the gas sensors we use, for example, tin oxide. In some of them, we use titanium dioxide. In some of them, we use copper oxide. So, and also not only the material, but also the structure. Then it depends on what you really want to get out of the structure. You might need to change the liquid that you're using. And also, if you are making a composite, it really depends on, like, for example, when we make carbon nanotube, ethanol is really good. But for example, when we made polymer, then we use methanol. Then when we add, it wasn't in my presentation, but in another work, we added palladium. Then for palladium, for example, we used toluene. So it really depends on what is the application and what is the structure you want. But generally, yes, the fabrication technique are quite similar.
Okay, thank you. And then one more question I have, like, what challenges did you face while doing flame spray pyrolysis, like for the synthesis of the materials?
Sure. So three challenges. The first one is the flame spray pyrolysis is only limited to metal oxide, and that is quite annoying because we wanted to make, let's say, gallium nitride, for example. We wanted to make silicon carbide, and we can never do that. And that's why we had to buy a CVD machine just to make other type of materials. Flame spray pyrolysis is only limited to metal oxide. The other challenge is when you make such a porous structure, then the structure is very fragile. Like if I make the structure and if I touch it, then the structure will damage. So we can only use it for gas sensors or light sensors because there is no physical interaction with the sensor. But for example, one of my students wanted to use the sensor in liquid. We wanted to detect, let's say, some elements in liquid. If you put the sensor in a liquid, the sensor will get damaged. So then again, we have to use other techniques. So flame spray pyrolysis is good if your sensor can detect light or gas. But if you want to detect something in liquid or something in solid, then it's not a very good technique.
Thank you very much, ma'am.
My pleasure.
Yeah, Professor Nasiri, excellent talk.
Thank you.
Yes. So I have one question for you. Like you mentioned zinc
Sure.
oxide. So
Yes.
there might be other wide band semiconductors also, which might be, similarly useful as in terms of the applications that you're going for. So did you try other materials as well besides zinc oxide?
Yeah, so I think gallium nitride could be a very good one, but unfortunately we could not make gallium nitride by flame spray pyrolysis. With flame spray pyrolysis, I use titanium dioxide as well, and also I use tin oxide as well. But for the UV photo detection, zinc oxide was the best, unless you wanted to have a bit deeper UV, not the deeper, like if you are interested in all UVA and UVB and UVC, all of them, then I think zinc oxide would be the best. But if you are more interested in detecting UVB rather than UVA, then titanium dioxide works better. So like, for example, some people ask me, for skin cancer, you need to distinguish between how much of UVA and how much of UVB. And zinc oxide is sensitive to the entire UV spectrum. So then we actually move to titanium dioxide, and then we put one sensor zinc oxide and one sensor combination of zinc oxide and titanium dioxide. And by doing this, we could distinguish how much of UVA and how much of UVB. But yeah, we actually thought about making gallium oxide by flame and then put it in the conversion furnace and convert it into gallium nitride by removing oxygen and in replacing it with nitrogen. But it wasn't that easy that we thought. So yeah, the limitation is that we cannot make nitride by the technique.
Thank you so much.
My pleasure.
Uh, yes. Hello, can you hear me?
Yes, I can.
Yes. Excellent talk, ma'am. I'm also working
Thank you.
on carbon nanofibers. So I just wanted to know that, like, my research is on biogenic CNF. So can biogenic CNF, which I have actually made from agricultural waste, can that be employed for the said purpose, what you are working on, like applications? Because biogenic
Yeah, so
CNF,
yeah.
yeah, they have porous
Mhm.
structures which are different. I mean, different agro waste resemble different structures. So can that directly be
Okay.
employed? Yeah.
So we can try. So what we can do, we can actually have them embedded into a polymeric solvent, and then we can spray the polymer, and then we can create fibers of polymer which has your fibers inside. So I assume that your fibers should be extremely tiny, so we can actually add them into that and then spray them and then make them perfectly aligned. But the only thing is that we have to think about what type of application we can use. In terms of fabrication, I think we can have them being used in some of the fabrication technique that we have, but then later we have to think about what is the final goal, what we're going to do about it, and then we use them for that particular application. So what is the application of your project?
Currently, I'm working on like fertilizer delivery. It is for fertilizers.
Okay.
Yeah. I have recently published a paper also in Elsevier regarding that, a chapter based on that. And I'm working on its different properties like water retention and whether it can serve as a very good carrier of fertilizer. And I'm getting positive results also.
Okay.
And I just liked
Okay,
the
wonderful.
applications which you said. So I was just thinking whether that biogenic CNF also can serve the same purpose, because the structural differences which a biogenic CNF has as compared to what we get from inorganic forms, there is a vast difference between that. So just our
Okay.
query, yeah.
Yeah, I have one student who is using CNF, but he's using CNF, he's adding it into his polymer, and then he used the CNF to make his polymer a bit more conductive. So that is the main app, because he's using the fibers of the polymer as a pressure sensor, and sometimes he doesn't get the signal that he wants. So he added carbon nanofibers into the solvent of the polymer before making polymer fibers. And now the polymers has a little bit of a CNF into that, and then that makes it a bit more conductive than it was before, and then enhances the signal that it has. So that could be one of the application. But if when you are using the CNF, if agglomeration is one of the challenges, then the technique we use could potentially solve that challenge, because we can suspend the CNF into the polymer, and then when we make them as the fibers, we can control how this CNF, instead of being agglomerated into each other, they kind of being perfectly aligned within the fibers. So if that one could potentially solve any of your problems, I think that could be a good project to explore.
Thank you, ma'am. I'll connect to you if I need some help regarding it. Thank you.
No worries, all good.
Any more questions from the participants?
One question. Hello, ma'am. Ma'am, after
Hi.
after synthesized material, how to transfer from substrate to flexible ID? What are
So
the
we don't
techniques?
transfer it. So we don't transfer it. We deposit the film directly on the flexible sensor. Okay. So if I had it, okay, let me see if I can find one for you and I can show it to you. So the problem before was that we could not put them in the oven because they melted in the oven. But now we solved the problem. We don't need to put them in the oven. Okay, let me show it to you. I don't know whether you see it or not, but this is the flexible substrate we have. Can you see it? Okay, so
Yes, ma'am.
now we put this one directly above the fire, but then the film is water cooled. So the substrate holder is constantly water cooling the substrate. And then if you put it very far from the fire, like 30 centimeters away from the fire, and then we have a very cold water going through the system, this one survives. So we don't need to even transfer. So we make the sensor on the top of a flexible substrate, and then we connect this one on a flexible PCB. So we don't need to transfer it. It is just the 2 pins connecting this one and this one attached to the flexible PCB.
Okay, thank you so much.
My pleasure.
Thank you, ma'am, for such an
My pleasure.
informative session.
Thank you so much.
I hope now the audience is well able to grasp the topic. So thank you, Professor Naseem Ashari, for an enlightening session. We are grateful to you for the time and efforts you took to share your experience with our IEEE community. I would now request everyone to please switch on their videos for a photo session.
And Professor Nasiri, on behalf of our IEEE Census Council and EDS community, we bid you heartfelt thanks. And the students have also prepared a small memento for you, and we will soon courier the same to you. And hopefully, in the near future, we'd like to welcome you physically at also our institute, Indian Institute of Technology, Indore, and would be loving to be your host. Thank you so much.
Thank you so much for having me, and thank you so much for your kind invitation. Yeah, absolutely. I mean, I would love to come over and visit it one day. Sure.
Thank you, ma'am.
Okay. Yes.
Moving on to our next plenary talk session, I would like to welcome Professor James Morris, Professor, Department of Electrical and Computer Engineering, Portland State University, USA. Here is a short bio about Professor James Morris. Jim is an ECE professor emeritus at Portland State University, Oregon, and an IEEE Life Fellow. He has BSc in 1965 and MSc Honours degree in Physics in 1967 from the University of Auckland, New Zealand, and a PhD in AA from the University of Saskatchewan, Canada, and was awarded a Doctor Honoris Causa degree by Bucharest Polytechnic University in 2015. He served as EE and ECE department chair at both Sunnybrington and Portland State. Jim has served the IEEE Electronics Packaging Society, EPS, and the IEEE Nanotechnology Council in multiple roles, but notably as EPS Treasurer and Conferences VP, and NTC Conferences VP, Finance VP, and President. He has been General Conference Chair of 6 conferences, including 3 in Electronics Packaging and Nano 2011, Nano 2020, and NMDC 2018, and Program Chair for others, most recently for NMDC 2023. He has co-authored 1 book on electronics packaging reliability and edited 5 more, including 2 on nanopackaging and co-edited 2 on nanoelectronics. His research interests have ranged from isotropic conductive adhesives nanopackaging, nanoelectronics simulation, and discontinuous thin metal films to automotive engine control, and has had numerous international visiting appointments, most notably with Nokia Fulbright in Finland, Erskine in New Zealand, and Royal Academy of Engineering in UK fellowship. Tim has taught continuously for 60 years and published 60 journal papers, 107 refereed conference papers, 33 book chapters, and 1 patent plus more than 80 other conference presentations. I would request Professor James Moritz to please take over the meeting. Sir, please.
Okay, can you hear me?
Yes, sir, you are audible.
Okay, I guess I click on share and this should bring up things. And now
Yes, we can see the slide.
I'm trying to figure out, oh, here we are. Okay. Thank you for inviting me, and it's my pleasure to be here to talk about something that has interested me for on and off for about 50 years. So I will start straight away because time is limited. And okay, most of the things that I will be talking about were fabricated by thermal evaporation in a vacuum system, as shown over here schematically. By heating a source with the material, it evaporates, and the vacuum system enables it to have a long mean-free path, and it is deposited on a substrate up here. The other things are peripheral. Generally, we use, well, most of the things that I will talk about have been fabricated by this method, and I will indicate otherwise as we go. Typically, we use gold on glass because the adhesion is very weak, and the gold can form islands in the early stages of evaporation. And you can see the development of the films of interest here. This is early stages. You can see there's already been a little bit coalescence here with smaller islands in a ring around a larger one. As coalescence proceeds, then you start getting more islands starting in the gaps between the larger ones that where islands have been absorbed into these larger ones here. And the process continues here with secondary nucleation going on until the gold, in this case, or other metal, forms a continuous path across the substrate and acts as a normal metal. And this is sort of showing the process of coalescence. There's a capture distance which is characteristic of a metal substrate combination. It's temperature dependent as diffusion increases. And then as coalescence takes place, you can see small islands starting to fill in the gaps. In particular, it's shown that the mass of the deposited film the particles vary as the square of the size or diameter, showing that the particles are flattened and they're more oblate spheroids than the expected sphere. Nevertheless, most of the original theory was based on the assumption of spherical particles. So these islands, these films, conduct electricity even though there is no metallic, continuous metallic path through the film. And it does so by electron tunneling with an electrostatic charge and energy, which we'll talk about in a moment. So this is the variation of the film particle sizes and the gaps. This is the radius and the gaps for two different deposition rates. And the thing that I point out to you here is that the separation of the islands is approximately constant over some region until the film starts to become continuous. That's the consequence of the capture distance. And I will note later on, it's not clear whether the workers here were measuring the larger coalesced island sizes or the secondary nucleation sizes, and that can be important. So this is the form of conduction in the films like this, and they are similar to a semiconductor appearance, but of course the mechanism is totally different, and the activation energy is here it varies from 0.03 to 0.3 electron volts, but values up to 1 electron volt have been observed. So this is the basic idea in the past has been if there are in infinity islands, that the number of charged islands is a Boltzmann distribution given here. And so for islands of radius R and gaps S, this is for the activation energy is electrostatic, the work required to remove an electron to infinity, or in our case to a distance S away, being the gap. And it can be assisted by the electric field. This is more or less like a Schottky effect, though it's not exactly the same thing. And like a Schottky effect, eventually you get a square root dependence on the applied field F. So one of the first things to do is look at the measured activation energies from the slope of those plots that we saw on this last slide and compare them with theory. And this is done here. The different colors for low field, this becomes negligible, and this expression becomes this form here. So the different colors correspond to the films of different groups. The lines here for the relative dielectric constant 1 or 10, and one would expect that all of the plots would fall into this due varying for second order effects. So at least the slope is consistent here, and the dark blue and light blue and the green ones, these are for the same group, different temperatures, and the green group here, and the most consistent is here, except that it's outside these limits. And the suspicion is that on the previous plots on the previous page, that the island sizes were for the coalesced islands rather than secondary nucleation islands, which of course would dominate the properties. And in this case, if that's so, these would move, this plot here would move right in the middle to here. Another one, this is for sputtered aluminum films, and it's the only instance that I know of a sputtered film showing these properties. With the dielectric constant, more what is expected as 1.44. The electron tunneling term is the standard form here, where this is the work function of the metal, and the other terms are more or less conventional. So one of the experiments was to investigate the field effect versus the square root of the field. And a theoretical treatment gives agreement of at least of the form, although you can't directly compare the theoretical and experimental structures. But the electrostatic activation energy is the basis of the Coulomb block and hence single electron transistors. So that's well established. And over here we have the strain effect, where the resistance increases with positive stress applied to the film, as the linear expectation is here. The author suggests that this is where the activation energy starts to change under high stress, but that is not, that's been theoretically investigated, but there was no experimental verification. So this is all very well, and the problem is that many experiments don't meet the expectation of what I've just shown you, and particularly the resistance, it doesn't scale with film length. That would suggest maybe there's something going on with the contacts. There also the resistances are orders of magnitude less than predicted by the classical, this stands for Negebauer and Webb, the original proponents of the basic theory. And if you try and match the conduction to the tunneling theory and everything else, it's way off. And to force a fit, you have to assume an effective electron mass 1,000th of the rest mass, which is ridiculous. Also, there's this suggestion that the observed activation energies up to 1 electron volt are much greater than KT at room temperature, and these are inconsistent with the Boltzmann assumption. Also, if you apply a bias, if you look at this as a capacitor, then if you apply a bias to the rear of the substrate, then this capacitor effect should pour charge into this film and swamp the Boltzmann distribution, and to 10 volts there is negligible effect. There is some minor effect, very minor, observed at higher voltages. The other thing is now we're talking about maybe contacts. We can look at the structure of the contacts. The film structures that I showed you were representative of typical work at the time, and they were by electron transmission, electron microscopy. And it's a practical difficulty that you can't really see structures near the contacts. But the atomic force microscope permits a little bit more in this area. And so while we can't get right to the contacts, we can see that the islands towards the contact are smaller with larger gaps than the films, the islands in the rest of the film. So the thing to take away from this is that near the contacts we have smaller islands and larger gaps. The reason is under debate, possibly due to contact heating during the deposition, or the atomic diffusion is mainly towards the contact and doesn't can't get away, and so basically the nucleation and growth dynamics are different. So also there was a Ukrainian group observed some interesting things on a film. For homogeneous films, i.e. ones with deposited where one would assume that the contact the contact structure near the contacts would be the same at both ends. It was observed that the electric field here near the positive contact was always greater than at the negative contact. Just going to try something. Okay. That's a little bit better for me. I'm not sure that if this, you can see exactly what I'm seeing here, but I wanted to get a bit more view. Okay, so that's for homogeneous. If we have inhomogeneous films, that means like here, the contacts at the two ends are different. It's a little bit difficult to compare this one with this one, but suffice to say that they're obviously different. And if we have the wider gaps like here at the positive end, remember that the positive end field is always greater, then we get a distribution like this. And if the opposite end is positive, we've got wider gaps at this end and the greater field at the positive end, and we have this sort of distribution. I have to say at this point that these results from the single group have not been verified experimentally by others. In this case, we end up with a diode effect. We get a different resistance in this case from this case, and although it's a diode effect in the sense that the two resistances or currents in the two directions are different. Okay, there's AC conduction should be an obvious thing to test, and it was There are results early on in the study of these films. Some of the earliest results had AC measurements. And so if you had a square film here, the resistance of the gap and the capacitance of the island, which was related to the activation energy, should be the same of the films for a square film, the same overall as for a single one, assuming everything is ideal. In fact, if we look at the results here, focusing on this corner frequency here, we get a corner frequency of by radian per second. If I think it was this one. Anyway, this gives us getting the resistance from these values here and the corner frequency from this, we end up with these values for the resistance and capacitance. But the film activation energy was 0.86 electron volts, which should be related to the capacitance, and that gives us a capacitance of 10 to the minus 19 farads. So that's way out. But the ratio of these two results is interesting, because this 20 puff over 10 to the minus 19 is about 2 by 10 to the 8, or actually 10 to 2 by 10 to the 8. And that's about the order of the number of islands along this contact. If you factor in the nature of the contact and there being two capacitances involved, then this is a very feasible number. So using this one, this value, we then get the gap resistance, tunneling resistance, about 2 by 10 to the 18 ohms for a single gap. And now, of course, there's lots of these in parallel. And so this can be converted to a cold plot or a Nyquist plot, as it's known in various texts. We get this sort of a shape, which can be converted to this equivalent circuit. And this shows us two different resistances and capacitances at the ends. The higher resistance, the higher tunneling resistance corresponding to a larger capacitance, island capacitance, with really nothing much other than a single resistance, lower resistance in the bulk of the film here. So all of the action is at the contacts. So what we do next is see if we can create the different structure at the two ends. And we can do this by offsetting the source like this, and this pre-deposited contact here effectively acts as a mask. And so the deposited amount of gold here is less than in this contact here. And so with a small offset, L in the figure being 1 cent, because I'm talking inches here, 1 inch, with the distance here 6 inches, we get something like looks like this. And sorry, the equivalent circuit here, it's relating to this plot here. So if we really push this up, so this is film here is with no offset. This would be the one that we had on the previous slide with 1 inch, 2 inches, and then 3, 4, and 5. These ones here, and we look like it looks like a sort of a resonance here. And these are the cold plots and various other plots from these results. So moving on to that, to switching effects. Switching in the discontinuous thin films was generally regarded as destructive. And so the first cermets have a very, very similar structure. A cermet, the term cer for ceramic and met for metal, it's metal ceramic composites. And this is some results for a gold polymer composite, which can be regarded as a three-dimensional discontinuous film. And these films were stable, and so they were run for about 20,000 cycles without any problems. There's some variation on the threshold shown here, but it's basically, this is the normal, and then the application of a sufficient field converts to a lower resistance. So I don't have the structure here, but this is something from a very aggregated film, which was converted to an inhomogeneous film by the application of a large voltage. And since the, well, for various reasons, maybe because the film was very, very agglomerated, we had stable switching. And you can see here that this is, it was, the contact structure was changed at one end, presumably the positive end, by the application of a high field. And then we had this diode effect here, plus switching, which was inconsistent from cycle to cycle, but continued stably without destroying the film. So going now to the fact that we've got a lot of things that we can't explain and some indication of contact effects. Okay, and the implication of contact effect behavior. This is a model that was proposed, and the idea is that charge generation occurs at the electrodes. This figure is, these are the islands, and this is the potential barrier between the islands. The arrows show electron flow, and we have electron injection to a negative island, sorry, a neutral island here, and hole injection to at this contact. Two things here. The hole injection is, of course, a neutral island giving up an electron to the electrode here. And where I show arrows in the gap in the islands here, that's the change in the Fermi level due to the process. And we really were concentrated on charge separation in the bulk of the film. Now, I've used the term hole in there, and don't be confused. This is not a hole like in a semiconductor. I just can't come up with a better name for a positively charged island. So then we have recombination, hold and extraction. So this is a positive island, and an electron here recombines with that, and this is charge recombination, and similarly electron extraction at the positive electrode. And we can have electron hole recombination in the bulk of the film. And then the basic transport in the bulk of the film, remember that low resistance in the equivalent circuit. This is basically just an electron hopping from a one charged island to a neutral, which becomes charged negatively, and so on. And so to a forced order, this increases the system energy, this decreases it, and this produces no change. There are second order effects that could complicate this, but let's keep things simple for the moment. Okay, now on the basis of that model, simulations were run. And I have two cases. In the first case, case A, the islands, well, the simulation was for 100 by 100 islands, and they are all 3 nanometer islands with 3 nanometer gaps, except the row of islands at the end here, which were 1 nanometer diameter and a 5 nanometer gap. So it's still on a 6 nanometer grid. And case A is when this is the negative end and this is the positive end. And you can see here the large, this is a linear scale at very low voltages. And you can see the big voltage drop at the positive end. And then there's a smaller but defined negative drop, voltage drop at the negative end. So this is just to show this once on a linear scale. The other things that I will show are all going to be log scale. So that's to be kept in mind. And so this is the very busy slide. This is case A over here, and this is the plot that we just saw on the last slide, but on a log scale, log voltage scale. And the plots up here are the center column of islands and the average distribution, and these at the 2 sides of the film. And this is for a case B is for the positive voltage at the small island, large gap end. And so we can see this is predicts a diode effect almost exactly numerically the same as the experimental one that what I showed earlier, but that's just a coincidence. This is for case B. We have the big voltage drop here. And remembering this is log scale, this is a small voltage drop here. These are plotted on the same scale. Yes, and in this case, we have a very much larger space charge at this end here, than on the other case here, where this is the positive end. And so it's positive in this case, but negative at this place, this end. The other thing is, this is all consistent with the model. The other thing is the transient step in the simulation starts off with only a couple of islands in the film, so a very, very low current, and that increases steadily to an equilibrium, which is what we measure normally. So this is the prediction of the classical theory. This is the normal experimental result. So this is like the increase of current with an applied field in an inductor. And so this effect is often termed pseudo-inductance. So we didn't expect to simulate switching, but nevertheless, this is the voltage that the simulations were run out. And if we increase that voltage, we got something funny going on here, but we actually have a lower, much lower resistance. This is the current, and that's roughly linear current voltage relationship here, but with a much lower resistance. If we examine the charge distribution in the film, these are the positive and negative charges across the film. This is at this critical end. This is the negative end with the gaps. Sorry, positive end with the gaps, I believe. And this is at this point here. And if we do the same thing, look at the distribution at this point, it's here. And this charge, space charge distribution has disappeared. So the working hypothesis is that when this voltage is exceeded, the potential barrier at the end of the film disappears, and there is no longer any impediment to charge transfer from the contact into the film. This is needs further study, both in simulations and trying to do it experimentally. So, okay. So further research needs to have a fabrication that produces uniform, reproducible, and stable structures. The deposition technique that I have described produces, is irreproducible. So a lot of experiments were done by samples side by side, so that presumably the films would be the same, and one changed the conditions on one side from those on the other. So that's the reproducibility. The uniformity is necessary to be able to model things and have any chance of being representative of real films. And they need to be stable. The islands continue to coalesce due to diffusion on the substrate. And there's some thought that the application of electric field might encourage coalescence in the field-induced coalescence. But that's also not been, it's been, people have performed experiments, but they're not conclusive. So anyway, the idea is that we need another form of reduction. The sputtered films that I mentioned and showed possibly will improve the situation, but I doubt if it will completely yield completely satisfactory films for further study. So there's a number of possibilities here. The sputter deposition I mentioned. We try to do standing wave fields, but the numbers never work out for either optical or mechanical standing waves. And E-beams have not been able to get to the size of the islands that we want. I haven't emphasized this, but on the first couple of slides I showed, if you look at the graph, the axis, these dimensions of the films are average thickness from 1 nanometer to 10 nanometers, for example. So there were atomic force microscope possibilities for deposition, whether by oxidation and nanoimprinting of a silicon substrate or other means. So I will cover a couple of these and then move on to the self-assembly of colloidal nanoparticles, which I think will offer the best hope. Oh, this is the sputtered film that I had. I didn't realize that I decided to leave this in here. You can see the growth of the islands here going this way and until they actually retain their discontinuity until very extreme thicknesses. Note this, the axis this way is microns or tends to be larger than the axis this way. So these islands here are actually probably flattened disks, which is not obvious for, or oblate spheroids, which is not obvious just looking at these things. So this is the idea for AFM deposition. The idea is that chromium is a sort of a atomic glue. It's often described as a barrier material against atomic diffusion, but in fact it will adhere to metals and stabilize them. And so here, if we can deposit seeds of chromium and then deposit the gold on top of these, then we can get stable islands stuck to the gold substrate by chromium and with gold over the top. And so this is one such island. And I remember what I said about the axes. This is angstroms high, but microns wide. And the problem is we can use a reverse bias diode here to define a small current. So if we can keep a current to a nanoamp, we still have to pulse this AFM tip, or bring this up to it, or something else, or pulse the voltage with about a nanosecond period. So that's should be doable. We didn't get that far. The other thing is to define nucleation sites by atomic force microscope, oxidation on silicon, and then etch the silicon dioxide away. The oxide growth extends into the silicon substrate, so this process will leave etched pits in the silicon surface on a pattern described by the AFM. And then one would have to have sufficient pits, if you like, that you could then reoxidize the silicon to form a substrate insulating surface and grow islands in defined positions. So when I was talking about this, we made these islands. You may be able to see them here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we were able to control the position. But as I said, we need to go much smaller sizes. Actually, sizes where we would probably not be able to see them. Okay, the problem with this is the raster scan of the AFM means that each site is being individually processed. And so that's not really good for production in the long term. So it's make me not worthwhile pursuing other than for basic research. And there's control issues as described here. Some other ideas, I mentioned the laser standing wave fields. EBM lithography has insufficient resolution. If you try and put nanospheres on the surface and for them to act as a mask, you need 5 nanoparticles. You need 10 nanometer spheres to get 5 nanometer particles with 10 nanometer gaps, which is pushing this structure, and this is beyond current capabilities. Now, this is the colloidal nanoparticles idea. Colloidal nanoparticles, we can generate nanoparticles by precipitation or other techniques from solution. Generally, the size distribution of these is too wide, but then you can self-assemble them on a 2D insulating surface. The advantage of all of these here is that you have a polymer encapsulation to stop the nanoparticles from coalescing, and these typically are monolayers, so they would yield constant nanoparticle gaps. And so we should be able to have accurate reproducibility on one of the parameters at least. So moving on from this idea, this is some work, fabrication of freestanding 7 nanometer gold nanoparticle films shown here. And these little things here are representing the polymer monolayer. And this work was in pursuit of a strain gauge, a strain sensor study. But the people doing this also measured and showed that the films that they got obeyed this relationship that we started with. So these nanoparticle gaps would be controlled by the polymer coatings, very uniform for tunneling. The question is, can we get small enough particles for measurable activation energies? And at least if they're not quite uniform, we would know the distributions which we could plug into models. And if we went the 3-dimensional road, then we could go vertically and have different size particles to check on our simulations in that way. So this looks like the way to go. And so it should be I'm being when I've paused at odd intervals, I've been checking my timer, which you can now hear going off. So I will stop that, and we should be right at the 50-minute mark. So just as a summary, we've looked at the discontinuous metal films in the classical conduction model and the anomalies which that presents in trying to explain experimental results. Those experimental results point to a contact injection model which has been simulated, and these simulations explain pretty much, well, I would say all of the experimental observations, not numerically because the simulations are for very idealized structures, but hopefully we can extend those to more realistic structures in the future. But for reliable experimental results which can be interpreted numerically and compared with theory, we need structural control better than we've had to date. And my prediction is that polymer coated nanoparticles is the best bet to achieve that. Okay, and all of these phenomena described here should exist in the 3D metal insulator composites as well. And so that's another way of doing it and trying to, for example, control the structures with different island sizes in a metal insulator composite. So some references there. This is the recent one, or most recent one, 2022. And further back, 77, was a review of the field at the time. And there's a couple of ones here that mention the model. That's the only reason for putting these in here. Okay, I am open for questions if anyone has any.
Thank you, sir, for such an enlightening session. The session is now open for question answers. I would request the participants to switch on their audio and video and then ask the queries to the expert by first introducing themselves.
Hi, Pudam. May I ask one question?
Yes, certainly.
Hi, Jim. It was nice meeting with you, but however, it is over this virtual network platform. So, and first of all, many thanks to you for accepting our invitation to join out of your busy schedule to deliver a wonderful lecture in this platform. So next time, probably we're hoping to meet with you physically at IIT Indore campus as well. So basically, it will be wonderful for many of us and our students to interact with you and learn many things from you. So rather than questions, like I wanted to just give you our heartfelt thanks regarding the same. Thank you so much.
If I can comment, I've been to India only once for a conference, and I would like to go again, but it's a long way away. But there is a conference, a nanotechnology conference, if I can do a plug, IEEE Nanomaterials and Devices Conference, NMDC as it's known, will be in New Delhi next year, sometime in October, probably. I don't have those details.
Okay. Yeah, that time will be wonderful to meet with you. This time our team participated in IEEE NTC, like nanotechnology summit that was held in Spain. So yes,
that's nano. That was nano this year.
Yes, this year.
And NMDC is the second flagship conference, if you like. It's typically a little smaller. I think last year it had 300 plus attendees.
Okay.
In Italy. This year will be smaller. It usually runs about 180. So we have big hopes for a big turnout in India next year. It's run by, I think, IIT Indore.
Yes.
Anyway, okay.
Yes. Yes, we are running 3 different societies: IEEE EDS, that is the main chapter, and 2 student council chapter also we are running, IEEE NTC and IEEE Sensors Council student chapter. So we are running 3 from our research group at IIT Indore.
Well, on the work here, applications include, of course, strain gauges that I mentioned, and also palladium thin films can be a sensitive hydrogen sensor. And hydrogen sensors, of course, can be used as indicators, early indicators of corrosion. So there's applications there, and potentially in switching, but with a lot of work to go, and also I'm sort of thinking of another one possibly, but I don't think the numbers will work out for practical use. The other thing is that practical single electron transistors can be with multiple islands. And that's one way of reaching a room temperature single electron transistor. And the other way is to get down to the dimensions of these islands, because most of the single electron transistor work was done at low temperatures with bigger islands. But the other thing is that this conduction theory, if you get beyond a single island for a single electron transistor, the model that we've established here should be applicable to those structures as well. And so that might be a way of simulating the multi-island single electron transistors.
Thank you so much. So I'll be requesting now, Poonam, you please go ahead with your question answer session. Thank you so much, James.
Yes, sir. So,
Sir, thank you, sir, for such a informative talk, sir. I have a question, sir. Sir, you talked about contact effects, sir. So, how does context makes any difference to check the value of resistances and capacitances in metal thin films?
In here, the capacity, the contact structure, the island structure right by the contacts seems to dominate the film properties, and by the injection and recombination processes that I described in the model. The thing is that, of course, most of these films, the contacts were deposited before the film, and it's an open question how much that they would affect the film properties if a film were deposited first and then the contacts deposited. Particularly if you could deposit the contacts at low temperature, so you wouldn't be encouraging islands to coalesce in the region of the contacts. But on a wider scale, these films are the early stages of fabrication of continuous metal films. And of course, that includes interconnects in integrated circuits. And so the islands, in fact, the things that eventually develop into crystals, grain sizes. And so controlling the island size also can be used to control the grain size in the continuous film. But the other thing here is that given this effect at the conductors, one would assume that the continuous film would have a slightly different structure at the contacts, even if in most of the IC cases, the contacts would be deposited afterwards rather than before. So there's all sorts of questions can be opened up about the broader impact of these structures on the continuous films used as interconnect in integrated circuits.
Okay, sir. Thank you for your answer.
By my watch and timing, I should be out of time. And
yes, sir. Due to the time constraint, we can only have one more question. So,
okay.
participants, is there any other question from the participants? sir, I guess no more questions. So
Okay, it sounds like you've got a bit more opportunity to stick to your original timetable.
yes, thank you, Professor Jeeves, for an enlightening session. I guess the participants are well now able to grasp the topic. Now, I would like to thank Professor James Morris for such an wonderful talk. We are grateful to you for invaluable time and efforts you took to share your experiences and insights with our IEEE community. I would now request everyone to please switch on their video for the photo session. Professor
Okay,
Morris, please.
I will sign off then, and thank you very much for your interest. I hope the audience found the talk interesting, and I hope some will be inspired to pursue the topic further. Okay, thank you very much.
Thank you, sir. Now we'll move forward for the lunch, and after the lunch, participants can join
Hello, good afternoon, sir.
So we will be starting in few minutes.
Yes, sir. Yes, sir. I'm just checking, sir. Okay, thank you.
Good afternoon, everyone. Myself, Poonam Bajoria. Welcome back after the lunch. So now let's move on for the oral presentation. These are the rules for the oral presentation. The allocated time for your presentation is 7 minutes and 2 minutes for question answers. Presenters should turn on their audio as well as video before starting their presentation. And attendees must ensure that their mic and video is turned off during the presentation. Now I would like to introduce our session chair, Dr. Nikita Vatstuhan, Professor, Sage University, Indore, and Dr. Dilesh Anand Srivastav, Professor, University of Allahabad, and our moderator for the session, Mr. Saurav Yadav. Mr. Saurav, you can please continue over the meeting.
Okay, so we will be starting with the first participant. So Savitri Prabhu, you can start the presentation.
Okay, sir. Thank you.
If you are unable to share the screen, you can also call us. We will share your screen. Okay, now it is visible.
Okay. A very good afternoon, everybody. My topic is advancement in emerging technologies for vital signs monitoring. I am going to develop one vital sign monitoring for household application. So that's why I chose this topic for today. So my guide is Dr. Muralidhar Bairi from Biomedical Engineering Department, Manipal Institute of Technology, and co-guide is Niranjan S, Professor and Head, Department of Biomedical Engineering. So basically, vital sign monitoring device. So it is used to monitor the vital signs. So before this, we will see what are vital signs. So what vital signs are the important physiological parameters which are used to um, used to represent patient status, health status. So these are very important parameters for the representation of healthy, physical health. So today we'll see which are the main important vital signs for the purpose of early disease detection or risk classification or risk identification. So according to me, based on the literature which I have done, so I found that main vital signs are blood pressure, body temperature, respiration rate, oxygen saturation. These are the main vital signs for for any detection of disease. So it mainly reflects body's physiological status, indicators of patient's health status, and we can find stability status of human body. So we think that only lab test reports or X-ray or CT scans are needed to find out the disease. But primary this indicators of detection of disease, they are mainly based on vital signs. So what are the advantages of monitoring vital signs? So we can identify risk levels easily. We can classify as it's a low risk or moderate risk and high risk. And disease prediction also, it's possible, by monitoring vital signs, and faster detection of emergencies. So based on the vital signs values, clinician can make decision faster. So he can, treat the patient immediately, and whatever, complications arise because of those disease or, any emergency condition, so that can be prevented. So nowadays we see that many people are suffering from chronic diseases. Chronic diseases. Namely we can mention it as a sugar or blood pressure or any other cancer. These are all long-term diseases. Which will affect human health. So so managing those diseases are very important. So once the patient manages these diseases, so he can live for for longer period. So management of chronic diseases also possible because of the vital signs monitoring. So patient can either go for hospital, or if a facility is there, he can monitor it at home itself. So that is the main advantages of vital sign monitoring. So as I mentioned earlier, so important vital signs are pulse rate, oxygen saturation, temperature, blood pressure, respiration rate. So we can see in the literature that these are the main vital signs. We have, other than this, we have many vital signs, but literature says that these are the main vitals for the prediction of any diseases, to find the emergencies, or to represent the health status. So now we'll see what are the disadvantages or what are the limitations of conventional vital sign monitoring devices. So the main limitation was there was many lead connections and cables, and there was it was depend on manual observation and record keeping. So there should be a chance of observational error. So while doing the observation, we should properly, we have to observe the readings and we should record it properly. Otherwise, it will lead to error. And it was more contact based systems, unless it is like most of the systems are contact based only, and it was inconvenient for the patient. So patient mobility was difficult, patient was not able to move, comfortably through these devices, and limited data storage. So those conventional vitals and monitoring faced many, these what to say drawbacks. So now the advancement of emerging technologies so made it easier for the clinician as well as the patient to monitor their health easily. So introduction to emerging technologies. So which are the main technologies we'll implement for vital signs monitoring? So wearable devices, all of we are using nowadays AI and ML in every application. Any applications, it is AI and ML is very
Savitri, please conclude your presentation. If time is going to be taken.
okay. 3D printing, blockchain, health monitoring, non-invasive, smart clothing, wireless technology, cloud computing, Internet of Things, mobile health apps, data analytics, and telehealth platforms. So these are the main emerging technologies which we implement for healthcare. So what are the impact of technological advancement? So continuous monitoring is possible because of the emerging technologies, increased accuracy, remote patient care, data integration, improved healthcare, resource optimization, and better patient outcomes. So these are the main impact of advanced technologies. So challenges. So in every system we have drawbacks as well as the we have benefits. So data privacy and security is the main challenge in advanced technology, accuracy and reliability, cost and accessibility. So for I know many of these technologies, they use internet, so there should be access of internet. Effective data management, overload of data should be avoided. Battery life, many of these devices use batteries. So battery life, we should increase the battery life. User education, so operating these devices need user education. Ethical consideration is also main challenge, and high initial investment. So future trends, along with all mentioned advanced technologies, now people are they are more interested, or they are more focusing on nanotechnology, 5G, improved connectivity, and multimodal monitoring, power harvesting, quantum computing, smart home health monitoring, biosensor, and remote patient monitoring. So I can conclude that significant vital signs are body temperature, heart rate, blood pressure, respiratory rate, and oxygen saturation. So vital signs monitoring systems are useful for health monitoring, disease prediction, and risk classification. So the implementation of these technologies, advanced technologies, they are very much helpful in vitals and monitoring to improve patient outcome. As technology continues to advance, vitals and monitoring will play an important role in personalized and preventive health care. So these are my references.
So thank you, Savitri.
Thank you. Thank you, sir.
Judges, do you have any questions?
Any questions?
Yes, Savitri,
Yes, sir.
could you
Yes, sir.
please tell me how blockchain could be helpful in vital sign monitoring?
Okay, sir. Like unlike other databases, so databases were based on the centralized system. So here it is blockchain is a decentralized one, and easily we can store the data in the form of blocks, and we are going to add each block, and we are storing the data. So we that limitation we can avoid, sir. Blockchain mainly for data storage and retrieval.
Okay, thank you.
Okay.
Next participant.
Okay, so coming on to next participant, Ashwini Dubey. बताइए. Ashwini Dubey. I think she has not joined the
meeting. So coming on to the next, Ankita Nemi. Ankita Nemi.
Hello, am I audible?
Hello. Yes, yes. You can share your slide and please switch on your camera.
Yes, I will switch on my camera. Ah. Am I still not audible, right? Am I not visible, right?
You are audible. Yes.
Audible but not visible.
Yes.
Okay, wait. I is visible, but I am not visible.
Your slides are visible now.
Slides are visible, but I am visible. Am I visible?
No.
Oh, but I am on my camera. Wait, I will stop it and I will join it.
I think you have locked your.
Huh? Wait.
You have locked your camera, I think. Just unlock your camera.
This one is for microphone.
You have locked your camera. There is a switch on your laptop to switch on your camera. Not on Google. You can directly start your presentation.
Can I start my presentation?
Yes.
Okay. My slides are visible? Hello?
No.
No? Now? Now it's visible?
Yeah, it is visible. It is visible now. You can start your
Okay.
presentation.
Shall I start my presentation?
Yep.
Okay. So, good afternoon, everyone. Myself, Ankita. I am a PhD scholar from PDPM IIITDM Jabalpur. Today, I am going to present the topic, effect of defects to tailor the structural and electronic properties of zigzag gallium nitride nanoribbons. So before going to the gallium nitride nanoribbons, basically we know that the first 2D material, that is graphene, which is being synthesized by Game and Novoselov in the year 2004. And this graphene is being exploited with the help of graphite, which is a 3D material. And this graphene has very unique properties, like it has high carrier mobility, high thermal conductivity, etc. But one intrinsic behavior that the graphene has, its semi-metallic behavior. So due to its semi-metallic band gap, this graphene cannot be used in many of the semiconductor devices. So as this graphene is made up of carbon, then this graphene can have its 0D form also, 1D, 2D and 3D. The 0D form is known as fullerene, 1D is carbon nanotube, 2D is graphene and 3D is known as graphite. So the 2D form, as the 2D form is semi-metallic in nature, so we are going for its low dimensional, that is nanoribbons. So basically what is nanoribbons? Nanoribbons are the ribbons which has width less than 100 nanometer, and it is being confined, means this nanoribbon is being confined in two direction, and it is being periodic in only one direction. And basically the nanoribbons can be have different edges. Like in this I have shown two types of nanoribbon. The left side is the zigzag nanoribbon. In this zigzag nanoribbon, you can see one periodic direction, and in that periodic direction, it had zigzag edges. And the other one is the armchair nanoribbon, which has arm-like edges, means two arm with a chair-like space. So this type of these two nanoribbons are there. And it has been seen that with the help of nanoribbons, the band gap also, they got also band gap 1D, and it is useful in many applications also. But as there are very much use of this GNRs, that is graphene nanoribbon, so I am interested in other 2D means materials. Other 2D materials means basically I am focusing on 3 and 5 group nanoribbons. As the graphene made up of carbon is a 4 group semiconductor. So their neighboring groups are 3 group and 5 group. So 3 belongs from this boron, aluminium, gallium, etc. And the 5 are nitrogen, phosphorus, arsenic, etc. So here I am going to discuss about one 3 group semiconductor, that is gallium, and one 5, that is nitrogen. So basically I will talk about gallium and nitrogen. So its structure is similar to that of graphene because they are the neighboring of this carbon. So their structure is also hexagonal shape, and they are also fabricated experimentally. And this gallium nitride in its bulk state, it is a direct band gap, wide band gap, and it's a direct band gap of 3.4 electron volt. So the gallium nitride can also be used for its optoelectronic properties in LED, etc. But this 3.4 electron volt is a high band gap, and we cannot use this in other device application purposes. So basically I will be talking about the tuning of these band gaps, means band gap engineering. So basically the methodology that I used is our DFT with the help of quantum ATK. So as these ribbons are 1D, so it is been periodic in one direction, that is Z axis, and X and Y are get confined, and a vacuum of 10 angstrom is being used here, and K point sampling is used as 1 cross 1 cross 50. Energy cutoff value is taken as 70 Rydberg, and the force between these atoms has been taken as 0.05 EV per angstrom. Now resultant discussion. In this, what the tuning I have done is I have taken the defect, that is vacancy defect. As we all know that this gallium nitride and all is being synthesized experimentally. So during experiments we got different type of defects, and this vacancy defect and this stone walls defects, it can cause vacancy defects. Means I have taken three type of possible configuration. First one is the perfect gallium nitride ribbon. Second one is I had made defect with the nitrogen, gallium. Sorry, the gallium defect, and we have written it vacancy at the rate gallium. Second one is nitrogen defect, means vacancy at the rate nitrogen. And the fourth possibility is both gallium and nitrogen atoms are not there. And the second one is stone wall defect. Stone wall defects basically is a topological transformation that can also occur during synthesis process. And in that topological transformation, generally you can see that the graphene is a means this hexagon, and hexagon. So when it is topologically rotated, they have this type of structure, means 2 heptagon and 2 pentagons. So now researchers has only predicted one type of topological transformation, that is 90 degree. But here I will in this presentation I will show other 2 types of rotations also, 180 degree and 270 degree. So basically after doing this, we have calculated some stability calculations. So here you can see about this vacancy stability calculations. In all the vacancy defects, we can see that it is a exothermic, means these materials are energetically feasible. Okay. In the second case for stone wall defects also, we can see that it is again exothermic, means it is stable and it is also energetically feasible. But the researchers have only predicted of 90 degree. We had predicted for 180 and 270. But in this case, it is very much nice to see that 180 and 270 is showing good results as compared to 90 degree. So we can also say that during experiment, this 180 and 270 can also be synthesized, means more preference of synthesizing in comparison to 90 degree. Next, we have calculated its Fermi level shift. We can see that the Fermi level shift, Fermi level in perfect is minus
You have 1 minute left
4.71.
only.
Okay, for gallium and nitrogen, you can see a shift in up direct. This is vacancy at the rate gallium. It is shifting downwards. This is N type. This is P type. So there is a shift of Fermi level also. Similarly, there is a change of band gap also. For perfect, we are getting band gap, but for vacancy, we are getting metallic. Similarly, for stone walls, there is a change in band gap and there is a reduction of band gap. We went for these bonding calculations. That is, what is the bond between gallium and nitrogen? We can see that the gallium and nitrogen has clear ionic bond, and between gallium it has clear covalent bond, and between nitrogen and hydrogen it has a covalent bond. Similarly, for predictions, again we have done the band structures calculations. Here you can see metallic as it is crossing, and here it is semiconductor, but it is reducing. So now For further configurations of metallic, we have done the spin polarized calculation. In the spin polarized calculations of metallic, we are getting, these are magnetic semiconductors. Means for one type of spin, like red spin, it is showing very low band gap, and for black spin, high band gap. Again, low band gap, high. Low band gap, high. So we can say that after tuning this, or after getting vacancy and defects and all, we are getting metallic band gap also. Again, we are getting magnetic semiconductor also. So these defects formed are energetically feasible, and vacancy defects are more stable, and there is a formulable shift n and p type behavior, and there is a band gap transitions also, and we are getting magnetic semiconductor properties which are useful for spintronic application as well as switches. These are references. Thank you for your time.
Okay, so Jadid, do you have any question?
बूटर से मंगा लूंगी.
Can you please explain why 180 to 270 degree? The diagram is
Yeah.
there, right? Please go to that diagram.
Yeah, this one.
Yeah, this one. This is
Yeah.
there is a bond is not there, right? Where you
Ma'am,
make this diagonal structure 180 degree to switching. Yes. The bond is there, right?
yeah.
Actually,
Bond
my question is this one. My question is this one. If we are rotating it to 90 to 180 degree and 180 to 270, again it is 90 degree gap. So what benefit you are getting?
Ma'am, we are actually stonewall defects means researchers have done only one rotation, that is 90. Okay, this we have done, but we are predicting some, these are not experimentally synthesized till now, but we are predicting that if we are rotating 180 and 270, then if we are calculating its stability factor, so we are seeing that the stability for 90 degree is minus 1.5 EV, whereas the stability for 180 and 270 degree is quite high in compared to minus 1.50. So we are predicting that if this type of material is going to synthesize, and if there is some type of defects in it like stone walls, then there will be more possibility of 270 degree rather than 90 degree. Okay, so we are just predicting it. It's not like experimentally synthesized. We are predicting that if we are rotating it, so it is feasible or not. If it has exothermic, means if it has endothermic formation.
Will the structure be same in every 90 degree rotation?
No, ma'am. Structure, this,
It
ma'am,
will change.
this.
If the hexagonal is supposed to be more stable, right?
Ma'am, it is not hexagonal also. When the defect is formed, this hexagon is being transformed to two heptagon and two pentagon. So already there is some transformation in actually, I am predicting that during synthesis there could be some defects like vacancy also, stone walls also. If there is a stone wall prediction, if there is a stone wall defects during synthesis, like it is not, we are not getting hexagonal, and in fact we are getting heptagon and pentagons type of structures, then in that if we are rotating more, so what type of structures we are getting? More feasible structures we are getting, like 180 or 270, what we will get quickly. So it is showing that 270, the structure is more quickly obtained in comparison to this 90 degree rotations. Like we are predicting it. It's not being synthesized yet.
Okay.
Any other questions, ma'am?
Nilesh, do you have any question?
Yes, Ankita.
Yes,
What
sir.
are the disadvantages of using gallium nitride? I have one basic question. Is the disadvantage of using gallium nitride? Do you know?
Disadvantage. Sir, one
Yes.
disadvantage is in the bulk, it is having wide band gap that we don't know, that we don't want. So we are tuning it to modify its band gap so that we will get a normal type of semiconductor, and we will use it in device applications. That I am generally, we are focusing on that bulk we are
Any
not
other
using.
thing? Any other technical specification other
Sir,
than this?
any other, sir? I don't know. I am
Basic
just
property that is. Okay, thank you.
Thank you, sir.
Next person.
Okay, thank you, Ankita Ninu. Now I call upon the stage the next participant, Ninu Maria Sani. You can share the
Sir.
screen now. Minu Maria.
Yes, sir. I'm
Can
sharing the
share it.
screen.
Okay. Also switch on your camera.
Yeah. Am I visible, sir?
Yes,
Hello?
you are visible. You can start your presentation.
Okay, sir. Good afternoon to all. I'm Meenu Maria Sani, working
Just
under
make
the
the
guidance of Dr.
presentation.
Ramesh.
Just make the full screen presentation.
It is in full screen, sir.
We are not able to see it in full screen.
Now, is it fine?
You can just use the slideshow on the bottom right corner.
Yeah, I have gone to a slideshow, but I don't know why it is not visible completely.
Okay, you can continue.
Okay, sir. Good afternoon to all. I'm Meenu Maria Sani, working under the guidance of Dr. Ramesh Tamanga, Professor, VIT Vellore. I would like to discuss on the topic spike rate dependent synaptic characteristics in lamellar multilayer alpha MO3 based two-terminal devices, efficient way to control the synaptic amplification. To start with, this is the roadmap of semiconductor technology, where we can see the past, present, and future of semiconductor technology. To start with, the transistor size was at 90 nanometer, and due to scaling, it has reached 7 nanometer at present, and we are expecting to decrease the transistor size even less than 1 nanometer. But here comes the limitation of Moore's law. According to Moore's law, the number of transistors in an integrated chip doubles every 2 years. But now, due to the scaling, there comes the issue of leakage current. Power consumption is reduced, and the device efficiency is also reduced. Then comes the need for some alternatives apart from the existing CMOS technology. And here comes the application of neuromorphic computing. Let's see what is the difference between von Neumann architecture and
Slides are not
neuromorphic architecture.
changing. Your slides are not changing. I think you have shared only PowerPoint. Just after presenting and while sharing, you just do complete screen sharing. Yeah, now it is changing.
Okay.
You can
Entire screen.
complete screen option is there. Yes, now you can share.
Is it fine, sir?
Yes, also just hide that part. Yeah, now it is visible.
Should I start from the beginning, sir?
You can start from here.
No, continue.
You start from here.
Hello?
Yeah,
Hello,
I
sir.
think yes.
Can I continue from here or start from beginning?
Continue from there, but your screen has stopped sharing.
It's fine now.
Yeah, you can start now.
So let's see what is the difference between von Neumann architecture and neuromorphic architecture. So in case of von Neumann architecture, this is the architecture which is used by the traditional computers. Here the memory and the processor is located at two different locations, so that if a data is to be processed, it has to be taken from the memory, processed, and returned back to the memory to process the next one. So this consumes a lot of time. And the processing here is sequential processing. But in case of neuromorphic architecture, here the memory and the processor is integrated at the same position, and the parallel processing is happening here. So even though big data is involved, the processing becomes easier. This is the one which is happening in our human brain. So now coming to the neuromorphic computing, let's see why our brain is a model system. Or in case of neuromorphic devices, actually we are trying to mimic the human. And also the brain has the ability of decision making. There are 10 raised to 11 neurons and 10 raised to 15 synapses in human brain. So a neuron, synapse, neuron junction forms the basic unit in
Your
human
slides
brain.
are, I think, the slides are again unshared. It is visible now.
So the basic unit forms the neuron synapse neuron junction. When an action potential reaches the presynaptic neuron and the synapse junction, a neurotransmitters are emitted, and this gets binded to the active sites of postsynaptic neuron, which emits postsynaptic signal. This is what we are observing. So a synapse is the connection point between the two neurons, and the strength of connection between the neurons can be modulated using different techniques. Coming to memristors, or for neuromorphic devices, memristors are having an MIM structure where two metal electrodes are sandwiched between a switching material. The structure is similar to neuron synapse neuron junction in case of human brain. So we can say that the brain is made up of memristors. Memristors are devices who stores the information in form of resistant states. The main principle of memristors is based on the formation and rupture of conduction filaments. In order to study the resistor switching characteristics of the memristors, normally we do basic IV sweeps, DC measurements, and also read-write erase measurements are also performed. Now coming to the neuromorphic measurements, we do pulsed measurements like single pulse measurement, double pulse measurement called as paired pulse facilitation and paired pulse depression, spike rate dependent plasticity measurement, and potentiation depression measurements for understanding the learning forgetting characteristics of the brain. Normally, we expect linear potentiation and depression, that is, the memorization should be linear, but what we are getting is a saturated potentiation and depression. So we have to determine the non-linearity factor to identify the deviation from linearity. Coming to my work is mainly based on MoO3, which is a transition metal oxide, where the oxygen atom bounded with central molybdenum transition metal. MoO3 is an N-type material with wide band gap greater than 3 electron volt. Apart from commonly studied MoS2 material, the band structure of bulk and monolayer MoO3 is found to be similar. But in case of MoS2, it is different in case of bulk and monolayer. MoO3 exists in 3 polymers. Out of them, alpha MoO3 is the stable orthorhombic phase. Beta and hexagonal MoO3 are the metastable phases. MO3 finds applications in resistor switching, lithium batteries, organic LEDs, and sensing, but our main focus is mainly based on resistor switching and neuromorphic application. Coming to the synthesis part, we have synthesized the material using MO3 powder as a precursor, and we have used chemical vapor deposition for the same at 750 degrees Celsius for 3 hours. From the X-ray diffraction analysis, we could find the prominent peaks at 020, 040, and 060 planes. From the UV visible spectroscopy using top load, we could find that the band gap of the synthesized material is found to be 3.22 electron volt. Here we can see the SCM image of the synthesized MO3 material. We can see that
you have 1 minute left.
The MO3 grown is having higher aspect ratio. From the TEM image, we can see that the MO3 material which is grown is of alpha MO3 phase. Now we have fabricated a device using interdigitated platinum electrode and broadcasted the synthesized material to the interdigitated electrode. We have studied the basic IV characteristic. To understand the conduction mechanism, a linear relationship was drawn between LNI versus LNU, and the LRS region is showing ohmic conduction, the HRS region is showing Schottky emission. To understand the stability and memory characteristics, we have performed read-write erase cycle. We have varied the pulse voltage, keeping the read voltage constant, and we found that for 1000 cycles, the device is showing good stability. Coming to the neuromorphic measurements, we have applied a single pulse under the optical stimulation of 375 nanometer LED, and what we are getting is an excitatory postsynaptic current. On observing the initial and final current, we can see the decay is faster, leading to short-term synaptic plasticity. It is a term used in psychology. Two types of plasticity is there, short-term and long-term. What we are aiming at is long-term, so that the memory retention will be larger. So we are getting short-term plasticities here. So we are giving multiple pulses by varying the frequency. At lower frequency of 1 Hertz, we could see the EPSC value is decreasing, but the EPSC value increases at higher frequency. So we can say there is a transition from long-term depression to long-term potentiation. The same is obtained here also. We are calculating A15. Here 15 pulses are there. So A15 by A1, the synaptic gain versus frequency is plotted. So below this cutoff value, we get long-term depression, and above that we are getting long-term potentiation and higher frequency. Now we are applying a pulse train for both potentiation and depression. 50 pulses each for potentiation and depression is given. For potentiation, we are giving negative pulse, and for depression, we are giving positive pulse. And we are calculating the non-linearity factor because we are expecting linear potentiation depression. To understand the deviation from linearity, we determine the non-linearity factor, and it is 0.69. So we could see, even if we change the pulse amplitude, we couldn't find any decrease in the non-linearity. Now, another what we have done is like we have varied the pulse voltage from 1.6 to 3.4 volt in both depression and potentiation. And on the consecutive pulses, we can see the delta I value is increasing. The delta I versus cycle number is given. At the 5th cycle, the delta value is increasing. We can say if we are giving multiple pulses, the memory retention can be increased. So coming to the conclusion, we have synthesized two-dimensional MO3 sheets using chemical vapor deposition technique, and the material conformation has been done using X-ray diffraction spectroscopy, and the band gap of the material is found to be 3.22 electron volt. We observed a large aspect ratio MO3 material, and we found that the synthesized material is alpha MO3. The device fabricated was using platinum interdigitated electrode, and the resistive switching and neuromorphic applications has been studied. This paper is published in RSC Advances. These are few of the references which I had gone through. Thank you.
Okay. Judges, do you have any questions?
Yes, could you please tell me why you have not used PVD, physical vapor deposition, in place you have used chemical vapor deposition?
I have used CVD for the synthesis.
So, can we use PVD also, physical vapor deposition? Are there some challenges of not using physical vapor deposition with MO orbits? Hello. Yes, please.
I have used the precursor MO3 powder itself and allowed the oxygen flow through the oxygen flow. So I wanted to grow 2D MO3 sheets. Like I got rod-like structures. In order to get that, I have done this procedure.
That's fine, but PVD can also do. Any challenge is there in PVD that we are going with the CVD?
I haven't tried PVD, sir.
Which is being done in high vacuum, which is in the vacuum. These are fabrication challenges. But your research is good.
I haven't tried PVD. I will check it.
CVD is fine, but this will know the differences. Okay, thank you. Next part.
Okay, now coming on to the next participant, Sudeepa Devi. Now you can share your presentation. And please switch on your camera also. Sudeepa Devi. I think she has not joined the link till now. So coming on to the next participation, Rahane Swati Namdeo.
Yes, sir.
Yeah, you can share your presentation.
Sure. Sir.
Also, please switch on your camera.
Yes. Just a minute. Sir, is my screen visible?
Yes, your screen is visible. Kindly share your slide.
Okay. Entire screen. Is it visible now?
Slides are not visible.
Okay, okay, fine, sir. I'll share it again.
You have to share the complete screen.
Yes, sir, yes.
Yeah.
Sir,
Yeah,
is it
now
visible now?
yes,
Okay.
yes. You can start your presentation
Okay.
now.
Yes, sir. Thank you, sir. Good afternoon, everyone. My name is Swati Rahane. I'm working as a PhD scholar in the Department of Physics, Savitribai Phule, Pune University, Pune, under the guidance of Professor Sandesh R. Zadkar. Today, I'll be presenting my research work entitled Structural and Optical Properties of Indium Alloyed CS2 AGBI CL6 double perovskites for Optoelectronic Applications. So this is the overview of my presentation. In first slide, I'll explain in introduction, I'll explain the general perovskite structure and motivation behind the work. After that, I'll explain the synthesis procedure of nanocrystals. In results and discussion section, I'll explain the structural optical properties of synthesized nanocrystals along with charge carrier dynamics in indium alloyed double perovskite materials, followed by conclusions and acknowledgements. So coming to the introduction part, actually perovskite is any material which has stoichiometry of ABX3, where A can be any organic or inorganic cation or group of elements like cesium, methyl ammonium or formamidinium. The B metal cation sites in hybrid perovskites, they are occupied by group 4 metals in divalent oxidation states like lead, tin and germanium. The halide anion has been the most effective component in the hybrid perovskites, and X is any halogen like chlorine, bromine or iodine with an oxidation state of 1, and the cubic symmetry is the ideal case for perovskites. So actually I am working on the double perovskite material, and the double perovskite material is nothing but the perovskite having unit cell twice to that of the general normal perovskite, single perovskite. So on the left hand side of this slide, I have shown the crystal structure of this double perovskite material, where cesium is positioned in the core of cuboctahedron, and there are the alternating AgCl6 and indium InCl6 or bismuth BiCl6 octahedron. So why I have chosen this particular family of materials for my study? Because the double perovskite materials have intrinsic property of self-trapping, and they have superior stability. Also, they show higher photoluminescence quantum yield of around 31.4%. They have large exciton binding energy and long self-trapped exciton decay lifetime. Also, the direct bandgap structure results in the efficient warm white light emission, which can be attributed to self-trapped excitons. So coming to the synthesis part, I have synthesized these nanocrystals by using simple anti-solvent recrystallization method, in which the metal prerequisite salts like cesium chloride, silver chloride, indium chloride and bismuth chloride were dissolved in 5 ml of DMSO at room temperature. The mixture is stirred until we get the clear solution. So this was my precursor solution. 100 microliter of this precursor solution was injected into isopropanol at room temperature and under vigorous stirring. So at this stage, I got precipitate, which I have centrifuged at around 4000 rpm for 4 minutes. And after that, the nanocrystals were washed with the mixture of IPA and toluene. The material was further characterized. So, to confirm the phase and purity of the synthesized nanocrystals, we have carried out the X-ray diffraction analysis. So, on the left hand side, I have shown the X-ray diffraction pattern of these synthesized nanocrystals, which shows the presence of multiple peaks as indicated by various HKL planes. So, the presence of these multiple peaks indicate that the material is polycrystalline in nature. Also, the very narrow FWHM of all the XRD peaks revealed that the nanocrystals are highly crystalline in nature, and they occupy the FM3 bar M cubic space group. So, from X-ray diffraction data, I have calculated various structural parameters like average crystallite size capital D, which is around 28 nanometers. Also, I have calculated dislocation density, strain, interplanar spacing small d, and the lattice constant, that is small a, and the values are listed in table. So, coming to the optical properties of these synthesized nanocrystals, here figure A shows the Raman spectrum of synthesized nanocrystals. The Raman spectrum was recorded using the excitation of 532 nanometer laser. The Raman spectrum shows three modes below 300 centimeter inverse. The mode at 114 centimeter inverse is ascribed to the breathing vibration of AgCl bond, whereas the other two modes are ascribed to the stretching vibration of AgCl6 octahedron. Figure B is the UV visible spectroscopy of this synthesized nanocrystals. So, absorption spectrum shows the peak at around 365 nanometer, which is an excitonic peak coming from the direct bismuth 6s to 6p transition. So from you, and also there is a long tail extended up to 700 nanometer, which is due to the sub band gap states present in the material. So from UV visible spectroscopy, we have calculated the band gap by using the Tok plot analysis by plotting alpha h nu square versus energy, and the direct band gap calculated from this UV visible spectroscopy data is 2.9 electron volts. Also, we have calculated Urbac energy by plotting ln of absorbance versus energy, and the Urbac energy is around 151 milli electron volts. Then figure E shows the PL spectrum of these nanocrystals. So the sample was excited with an excitation wavelength of 365 nanometers, and the broadband emission is getting for this sample, which consists of the emission from free excitons, defects, as well as self-trapped excitons. So the spectrum is deconvoluted into 4 peaks by using the Gaussian distribution. And figure F is the PLE, that is photoluminescence excitation spectrum of synthesized nanocrystals. The PLE is recorded at emission of 570 nanometers, and it shows two peaks around one around 325 nanometer and another at 370 nanometer. And from PLE we confirmed that the peak at 370 nanometer is due to the defects, and the peak at 325 is due to the bandage excitons. Then to determine or to study the charge carrier dynamics of these nanocrystals, we have carried out the TRPL, that is time
You have
resolved
1 minute left
photoluminescence
only.
measurement at emission of 420 as well as 580 nanometers. So for emission at 580, we have
You
fitted the
have 1
curve
minute
by
left only.
exponential. Sure, sir. I'll finish my presentation in 1 minute only. So the spectrum is fitted by using by exponential function, and the average lifetime is calculated by using formula shown on right hand side of this slide. So the calculated lifetime is 173.62 nanoseconds for emission at 570, and it is 65.71 for emission at 420 nanometers. Also, we have carried out temperature dependent PL measurements for this sample. So temperature dependent PL measurements show that the self-trapped exciton PL is becoming dominant over the free exciton PL when temperature is increased from 80 to 300. Also, the STE PL exhibited a blue shift while free exciton PL was unchanged as shown in this figure A. And ST peak profile is narrow at lower temperatures, and it is becoming broader at the higher temperatures. In figure B, we have plotted corrected intensity versus 1 by T graph, and it is fitted by using this Arrhenius equation shown on right hand side. And figure C is the FWHM square versus 1 by T plot to calculate the Hong-Rice parameter capital S, which gives the strength of electron phonon coupling in the material, and also the phonon energy, that is 14.7 MeV. So coming to the conclusions, we have successfully synthesized cubic phase nanocrystals by anti-solvent recrystallization method. XID and Raman measurements confirmed the pure cubic phase of nanocrystals. Absorption spectrum revealed an extended long tail, suggesting that the transition from subband gap states may originate from the surface defects. Also, there is a large Stokes shift as calculated from UV and PL, which is an indicative of presence of defects and self-trapping in the material. Also, higher value of Hongrice parameter confirms the strong electron phonon coupling in the material. TRPL data suggested that their violet and orange emissions, that is bandage and defect emission, originate from free exciton and ST respectively, and the material is potential candidate for photo detector as well as LED application. And this is the acknowledgement. So with this, let me thank you all for your kind attention. Thank you.
Yeah, thank you, Swati. Now, floor is open for questions for the guests.
Yes, Swati, as per your results,
Huh?
you have done your verifications till room temperature. I think.
Sorry, sir.
Your results are being verified till room temperature.
Yes, sir. From 80 Kelvin to up to 300 Kelvin.
The temperatures variation.
Yes, we have
So
varied the temperature from
variations.
80 to 300 at the interval of
So
10
that is
K.
till room temperature only.
Yes, sir, we can say that actually because it varies as per ambient conditions.
That is fine, but above room temperature, room temperature is the ideal condition.
Sir, can you
What
repeat
about
the
above
question?
room temperature?
Hello?
Above room temperature. What are the results above room temperature?
Sir, actually, what happens is if material is indirect band gap material, the self trapping is the intrinsic property of these materials, and the emission coming from the self trapped excitons is not we cannot identify it, or if we cannot detect it at room temperature. So we achieved low temperature using liquid nitrogen, and from 80 K to 300 K we have recorded.
Yes.
Low temperature PL at the interval of 10 K actually, but I have shown here at the interval of 20 K because if I use all the data, then data will be crowdy, so that's why I use this. And from that we have studied the strength of electron phonon coupling, and also the broadening and other contributions from defects and self-trapped excitons.
Okay, thank you, Swati. Next question, please.
Okay, now coming on to the next participant, Vishal Paul. Vishal Paul, now you can share your screen.
Yes, sir, I am present here.
Yeah, you can share your screen now.
Yes, I am sharing.
Please switch on your camera.
Camera is switched on. It is being connected. I am sharing. It is being connected.
Okay. Vishal Paul, your screen is not visible.
Yes, sir. Yes, sir. Yes, sir. I am trying to connect.
Yeah, it is visible now. Just share your entire screen.
Entire screen. It's not opening.
So if you have any issue, I can share on your behalf.
Yes, sir. Yes, sir. It will be more better. It will be more better. Share হচ্ছে নাকি?
Just wait, I'm sharing.
Sir, please see whether it is now it is coming.
No, it's not visible now.
It's not visible now.
Not yet.
Yes. Oh.
That's a lag.
I have shared the screen on your behalf. You can present now. Then you have to change the language.
If it is possible, please share it.
I
If
have
it is
shared.
possible, it is. You have shared.
Yes, sir.
Oh man.
You can start now.
But I am unable to see it. Yes. It has come. So, good afternoon. I am Dr. Vishaljit Paul, Assistant Professor of Electrical Engineering in the department and of the Institute, Narula Institute of Technology. So today I want to discuss about the virtual power plants. Markets means how the power is being traded here. So next slide. So what is the conception behind these virtual power plants? So mostly due to the global warming and due to the greenhouse gases in the atmosphere and all these pollution pollutants like carbon dioxide, carbon monoxide, methane, sulfur dioxide, nitrous oxide, all these poisonous gases prevent the coolness of this Earth. So due to this, there is a large amount of carbon footprints. So these carbon footprints will increase the rise of the ocean level, and most of the islands will be destroyed. So these are all due to the thermal power generation. This thermal power generation, that is our conventional power plants, this is due to the coal-based, oil-based and gas-based power plants mostly, and due to the environmental pollutions. So this sort of, we have studied another sort of energy resources that are known as renewable energy sources. So only renewable energy sources can change the total load scenario of this planet Earth. So this is one of the challenges. So the virtual power plants, how they integrate with the conventional ones, So lots of agreements in 1997 Kyoto Protocol Agreement and Paris Agreement. So all these agreements prevent the starting of the pollutions of this atmosphere. So another international agreements, new generating units. Now these virtual power plants means all these renewables, the battery storage, as well as the use of the electric vehicles. So all these will help us to produce the energy sources. So there will be a sort of the mixed generation. So new generating units to available the generation capability, the penetration. Now, what is the greatest challenge? One of the greatest challenge is, though these thermal power plants have high inertia, and the renewables, they have low inertia. So that wise, there is a large amount of frequency problem. Moreover, the renewables are very much uncertain. Their production level is uncertain. So they are also known as stochastic generating units, and they depend on the meteorological phenomena. So all these things we have to integrate. So the battery storage as well as the energy demand management. So the energy demand management, battery storage, as well as the cohesion between the units. So the thermal units will be used in place of the renewables. So all these things will help us to make the virtual power plants. Now through the virtual power plants, the facilitators can buy or sell the power. They can, when they earn the profit, so when the battery will be charged, when the battery will be discharged. So all these things are done through the programming. So that sort of programmings are known as stochastic programmings. As well as if we use the conventional, they are known as the deterministic programming. So the VPPs have very flexible demands that constitute the consumption assets, which can shift part of their energy. The part of the energy consumption means the demand management, and they are motivated according to the technical and economic aspects. So economic aspect, what is the price? What is the technical aspect? How much power to be sent? So all these things we have to. So this is a new concept, the virtual power plants. That means it is not virtual. It is physically there, but they are very small amount, and we don't know when they will be needed. So that's why the conception is there for the virtuality. So because conventionals are very much deterministic, because we have to pay the amount and we will be getting the amount. But the renewables, the operational cost is almost zero. There is only a fixed cost. So next slide, please. So the uncertainties. So what are the uncertainties? The uncertainties are the market prices and the available production. So we have to take the decision levels. So the optimal energy trading, so how much will be that it will be traded, all these parameters are set for the decision making algorithms, and we have to do the programming that is known as the stochastic programming, and that is also some sort of optimization, robust optimization. What is the maximum, the worst level optimization, worst level scenarios, we have to take it and we have to optimize it and calculate. Next slide. So, okay, sir, this is my area of research. I am doing research regarding the integration of the virtual power plants. So, this is the somewhat a little bit talk of around 7 minutes I have given. Thank you all. You can ask any sort of questions regarding this integrating renewables.
Sir, Vishwajit sir, your idea is good. However, do you have any model available?
Model
available for this virtual power plant, because it was only the
no,
idea.
sir. We are doing the economic aspects. We are seeing how much. Suppose a facilitator is providing us the battery storage, as well as the facilitator is providing electric vehicles. So he wants to make profit. So when he will be charging, when he will be discharging, so the discharging means the power will be sent to the grid, vehicle to grid and grid to vehicle. So V to G and G to V. So all these modes are there. So the facilitator wants to earn the profit. So at what time? So this modeling, mathematical modeling, we are guiding our students. We are developing the software. We are developing the programs, MATLAB programs, and we are publishing our papers. So recently we have published our, given our papers at Indicon, Audicon, Calcon. So all these IEEE conferences, we are providing papers. So last even NIT Meghalaya, we have published our papers. So likewise, we are doing work regarding our research work regarding all these things. So this is in power system, this is almost a new dimension. So today's world is want to have a pollution free environment. So the global warming, we have to dismiss the global warming. So one of the most important challenges of today's climate condition is global warming. So how to change the climate condition? So we last for 100 years, we are using the thermal power plants, coal-based, oil-based power plants. So we have to lessen all these power plants and we have to increase our renewables.
Okay, thank you. Thank you, Vishwajit.
Okay, sir.
Next
Thank you very much. Thank you.
Okay, thank you for your presentation, sir. Now coming on to the next participant, Haya, I am.
Yes, sir. Can I share my screen, sir?
Yes, you can share your screen and please switch on your camera.
Yes. I think I'm visible. Sir, is it visible?
Yes, it is visible. Just make it full screen and just click on hide.
I can't get you, sir.
Just click on the hide icon at stop sharing. Beside stop sharing, there is a hide option. Just click on that so that the slides are clearly visible. Yes.
Oh, okay.
Now you can start.
Able to get it.
Yeah, now you can start.
Yes, sir. My name is Zaim Daya. I'm a research scholar from NITTT at Chennai. I'm guided by Dr. S. Sasireka, Associate Professor from Department of CSE. My work is on context-based citation recommendation system.
Here, now in the recent years, research papers are published in different conferences and journals. So while writing a research paper, searching for the relevant references is a time-consuming process. Our objective of our project is to design a context-based citation recommendation system so that it able to explain the relationship between the citing and the cited paper, and also able to recommend the paper to the researchers. The scope of our project is in every research work, the base is the literature review. So the literature review will provide the gap in literature and the context for our own research, and find other people's working in our field. So this is the overflow. The user who are writing the research paper, this is the citing document, and this is the citing document. From that, the context, the surrounding context will be extracted and will be represented, and the other citing papers, that is the other references paper, from that the abstract, the title, or the context embedding, or the block diagram embedding will be extracted and will be represented. And using the models, the similarity or the relevant of the paper will be extracted by using either the similarity scores or the other techniques, and those will be listed. So based on the score, based on the top scores, those papers will be recommended to the users. Now, these are the basic classification techniques: content-based, collaborative filtering, hybrid method, and ontology. So these are the literature, some of the literature review. And the summary of my literature is various researchers has defined different parameters to find the relationship among the research papers. Different approaches such as collaborative filtering, graph convolution network, vector space model, and other deep learning algorithms are also involved. So usually key-based query is the most commonly used, but even that the context-based provide more accurate result, and the existing data set, it's not up to date, and the evaluation of the model can be carried out using the metrics like precision, recall, NDCG, MRR, MAP, which are the commonly used metrics. So these are the commonly used dataset: peer-read dataset, DPLP, SITSRX, RXX, SSCS. This is the overview of the algorithm taxonomy. The citation recommendation data features usually considered from the survey are the topic, the author's information, and the publications, and the keywords, and sometimes the abstracts. The data is usually represented using mainly by metrics-based, graph-based, and even the hybrid method also used. So the methodologies and the models commonly used are embedding, MLP, RNN. So the recommendation types are usually global and labels. Personalization, personalized and non-personalized. The local recommendation, the global recommendation is if you're considering the whole of the abstract or the whole of the paragraph or even the whole of the paper is the global citation recommendation model for providing the similarity score. And if you're considering only the surrounding context where it has to be cited is the local citation recommendation model. So from the survey, we are able to understand that the knowledge graph, compared to the traditional way of keyword searching, that the knowledge map provide a broad searching of broad searching. Broad matching based on the topic and the co-authors network graph. Based on that, we can able to provide still more recommendations. So the knowledge graph not only consider the citation count, but it also consider the appropriate context, and would provide the recommendation based on the domain specific knowledge. It can able to recommend the corresponding papers. So the knowledge graph are created by based on the some of the three methods: neural network enabled KG creation. Here the context will be given, it will be tokenized, and the tokenized context will be given to the neural network classifier. Here the classifier will extract the entity and the corresponding relationship, and the entity relationship will be once again further classified, and it will be given to the triple set. The triple set is it will make a formation of subject, predicate, and object, and on the triple set the CNN will be applied in order to provide an elaborate patterns of the triple set, and the feature maps which has been extracted will given to the score mechanism in order to identify the quality of the of the relevance paper, and the relevance entity and its relationship those will be represented in the form of the knowledge graph. We can able to visualize it. We can able to visualize it using the node as the entity and node as an entity and edges as the relationship. So the other method is NLP enabled KG creation. Here the input source is considered here is corporate text, ontology document, and knowledge bases. From that, the text will be given as an input to the tokenization. The tokenized sentences will be stemling, and POC tagging will be applied. POC is a part of speech where the tokenized sentence will be from that will be extracted the corresponding words in the form of noun or verb. From that we can able to get the meaningful phrases of the sentence, and from that the concept the domain can be recognized, and the raw data is further processed using the NLP pre-trained models, and the structured data will given as an input to the information extract where the key entity and the relationship will be extracted, and the classification will be carried out, which can be used for either report generation or question answering. So here the validation will be carried out using the label data from the human annotation domain expert in order to refine the models for better accuracy, and the knowledge graph will be drawn to organize the information that has been gathered. The third one is the rule learning based KG creation, where the sources from different the sources from
You have
different
1 minute
online
left.
sources will be. So
You have 1 minute left.
Sorry, sir. Just 2 minutes, sir. The sources which has been obtained from the online sources is of structures, unstructured, and even semi-structures. It has been processed in order to extract the entity and the relationship. It has been further processed using the logic connectives, so that and it will be in order to filter the irrelevant entities, and it will be stored in the form of triple storage, and it will be represented in the knowledge graph. The challenges which we are facing here are the cold start problem, scalability, explainability, and incorporating external context. These are the evaluation metrics that we are using in order to provide the accuracy of our model. Conclusion: when developing a personalized recommendation algorithm in order to tailoring the recommendation to individual user preferences and research goals, we are also planning to integrate the data from research grant, data sets, and experimental results, and also to provide user with explanation for the recommendation. These are the references. Thank you.
Is your system is prepared? Or have you done any analysis over your system? Or only ideas in there?
Sir, I can't get you, sir.
If your system is prepared, any kind of analysis you have done to test the papers of similar domain?
He's asking about the is there any physical implementation of the methodology you have done on some paper which is already been published?
So while we are writing our research paper or our literature survey, a keyword usually in Google Scholar, or if we consider any AI tool, they'll be mainly based on the keyword search. So as a student of the first year, I may find it difficult to place all the keywords. I may not be familiar with all the keywords. So by using the context, I can get the broad idea of the current research work that has been going on during the particular period, sir.
But if we say the similar thing is ChatGPT is also doing, although that is not valid one, but it is
Sir,
available.
actually,
How it is different
ChatGPT
from the chat?
usually.
It is
Sir,
all
actually,
taking content, keyword, everything that is taking.
actually, in
Have you think
ChatGPT.
to? Okay. Yes, please explain.
Sir, actually, ChatGPT will provide the content where the research paper has the highest citation count. So it won't consider the paper which has no citation count. So based on our context, even the paper which don't have a citation count can also be appropriate to our work now, sir.
You can train the ChatGPT. As much as you will train the ChatGPT, it will work accordingly. Anyway, your idea is good, but it was more good to possible to evaluate as if you have presented any analysis also.
Okay, sir.
Okay, thank you. Next participant.
Thank you, sir.
Okay. Now, Thirumuran. Hello. Thirumuran, you can now share your screen. I think he has not joined till now. So the next participant, Trishala Desai. Trishala Desai.
Yes, sir. I'm here.
Yeah.
Am I audible?
Yes, yes. You can share your screen and switch
Yes,
on
yes.
your camera also.
Yeah, sure. Hello everyone, I'm Trishula Desai from Mahendra University, Hyderabad, and I'll be talking about the novel precursor synthesis for solution processable deposition of low-dimensional TMDCs, that is transition metal dichalcogenides for flexible electronics. So, is my screen visible?
Yes, it is visible.
Yeah. So this will be the flow of my presentation. So as we are in the era of computing and all, so semiconductors are everywhere, as we know, in household appliances, industrial, medical applications, computers and cell phones, we are using it daily. So there, these semiconductors need some semiconducting materials. So the novel material innovation is the crucial technological need nowadays, and coming towards the flexible electronics, one dimensional, two dimensional and hybrid nanomaterials are specifically focused on these days. So for flexible electronics purpose, the current focus is on the fabrication of devices which are really light in weight, deformable, energy efficient, and which also has multifunctionality in nature. So comparing to the transition metal or like metal oxides, I'm going to talk about the transition metal dichalcogenide semiconductors. These has the formula like MXEY, where M stands for transition metals from the periodic table and E stands for the sulfides, selenides or tellurides, which has the combination of metal as well as chalcogenide material. So these materials are the layered semiconductor materials and has the tunable band gap, which can be tuned based on the structural or the properties, synthesis properties of this material. These are the inorganic analogs of graphene and can be formed or synthesized into monolayer or few layer TMDCs, which can be semiconducting, which can have semiconducting properties. And they show a unique electronic, structural, and optical properties similar to graphene and which are a substitute to graphene these days. So these low-dimensional transition metal dichalcogenides can be fabricated by different routes. So the exfoliation and chemical vapor deposition, these are the two specifically focused routes for transition metal or like low-dimensional TMDC synthesis these days. But the issue with the exfoliation, like mechanical or maybe chemical exfoliation, is these are not suitable for mass production of the semiconducting devices or for the chip designing. And coming towards the chemical vapor deposition, it has the high temperature need, or where the MO3 or deposition and annealing with the sulfur or selenide sulfurization process is needed further, which takes like around 700-750 degrees Celsius. So these temperatures are not compatible with the thermal budget of the flexible substrate like the PET or polyamide substrates. So nanoelectronics needs an alternative and scalable low temperature growth methods. So we are introducing a new method where we are designing single source molecular precursor, where the precursor has been designed initially. It is a pre-designed molecular entity, and then it can be deposited directly on the flexible substrate. So these single molecular precursors are the combination of molecular or salt containing both the metals and chalcogen in a single moiety. So using a hydrothermal deposition method, like solvothermal deposition method, this precursor has been just dissolved in one of the solvent like ethylene glycol, and at very low temperature like 130 degrees Celsius and at 8 hours of deposition duration, we are able to deposit this material on the flexible substrate. So the low temperature, this is a very low and cost effective, low temperature and cost effective route for the deposition of metal sulfides, which is suitable for flexible substrates. So this is the synthesis, like the design precursor formula, like how we have done this. So one of the metal precursor and the dialkyl dithiophosphate has been designed, which forms a bonding with the nickel metal surface metal as it is before, and the bondings were confirmed with the FTIR and NMR techniques. Further, the advantages of this single source precursor for the solution processable method are like they have the preformed metal and sulfur bonds, and low temperature and binder free deposition on the substrates can be done with these using this precursor. And this is compatible with the thermal budget of the flexible substrates such as PET and polyamide, and this is a scalable and industrially compatible route compared to exfoliation and CVD method. So we have deposited nickel disulfide on the flexible substrate as I have shown it here, and then we have studied its structural and morphological characterization, where we found that the cubic structure of NiS2 phase without any impure or the other phases of nickel sulfide were observed. It was a pure complete NiS2 phase observed. And the particle size, the absorbance studies show that the absorbance is in the UV visible region from 200 to 350 nanometer, and the band gap calculated was 3.67 electron volt. So there's a blue shift here attributes the formation of very small in size nanoparticles, and the band gap has been shifted towards
have 1 minute left.
dielectric, spherical morphology, and the size was around 50 to 100 nanometer. Further, we have studied the resistor switching properties of these devices, where on the deposited layer of nickel disulfide, the gold was patterned as the top electrode, and it shows the reliable and reproducible bipolar resistor switching in the very low operating voltages, that is around 3 volt region. And then we have also studied the device size, that is where the radius of the top electrode was varied and the switching properties were studied. So in switching mechanism, it was observed that the vacancies, sulfur vacancies, are created within the active layer, and the transfer of the vacancies takes place, where the switching of the device takes place from high resistance state to low resistance state. Further, we have also studied, sorry for it. Are you able to see my screen?
Yes.
Yeah. So the flexibility test where the device in bending state was studied for and showed almost similar properties as that with the flat surface. Also, we have studied the statistical evolution, where we studied the differentiation between the set and reset voltages and on-off current. Further, the same device where the nickel sulfide is deposited on the flexible substrate was studied, explored as the breath monitoring system. Are you able to see my screen?
I think your screen is hanging.
Yeah, it got stuck, I guess.
Okay, it's fine. Vishala, what are the advantages of having bipolar resistor switching?
What are the advantages?
Yes, bipolar resistor switching.
Yeah, bipolar resistor switching can give us the switching in the both the polarities, like positive and negative, which used for storing the data in the form of high resistance state and low resistance state further, like 0 and 1 logic.
In respect to your device fabrication, I'm asking.
With respect to device fabrication.
Yes. What is the size of your?
Sorry. Yes, sir.
Yes,
What,
sir.
at what dimensions you upload? Dimensions.
Size of the film you are asking, sir?
Yes.
It's 0.8 microns.
0.8 microns. That's fine.
Yes.
So,
Yeah.
in respect to that bipolar resistive switching,
Yes, sir.
you explain the advantage at 0.8 micron.
Hmm.
Why
Sorry,
they
I
are
didn't
getting
get the
bipolar
question.
resistor switching?
Bipolar resistor switching, we tried
Basic.
switching.
So the basics of getting bipolar resistor.
Actually, we biased it in the positive to negative region.
Okay, thank you.
Thank you.
Next participant.
Okay, so thank you, Trishala. Now coming on to the next participant, Priyala Nandini. Now you can share your screen. Shrilaya Nandini. Please share your screen is sharing. Please share your slides and also switch on your camera.
Sir, is it visible, sir?
Yes, it is visible. Switch on your camera if possible.
Yes, sir. Yes, sir. Just a minute.
Make the slide full screen.
Yes, sir. Sir, is it visible, sir?
Yes, it is visible.
Sir, what about the cam?
You can start now. Camera it is not visible, but you can start now.
Okay, sir.
I think it is the PPT is not visible. Just share your whole screen. You have shared only, I think, presentation. Share your whole screen.
Sir, is it visible? And what about the cam, sir?
Camera is open. Share your whole screen. Stop sharing and yeah, it is visible now. Just make it full screen.
Yes, sir. Yes, sir.
No, just go on the right corner. You will be having a slideshow option.
Yes, sir. Can I
Before 75% also. Just
start?
click on that. Yeah, you can start.
Yes, sir. Good afternoon, everyone. It's a pleasure to connect with you virtual today. My name is Siriala Nandini and I'm from EC Department 3rd year from Savita Institute of Medical and Technical Science. And I'm today excited to talk to you about the smartphone powered food diagnostic innovating the future food safety. So, which is my ongoing research under the Professor of Cyril Robinson. So, coming to the introduction, smartphone powered diagnostic is the revolutionization how we ensure the food safety. By combining the mobile technology with the advanced sensor, this innovation makes the food
faster testing, and most accessible and cost effective, shaping the safer future to the global food system. So in this work, we consider a Samsung Galaxy smartphone is used as LFIA. It is a lateral flow immunoassay reader together with a close-up and lens and a wide LED to improve the detection limit. So we can observe here the slide. So observing these figures, we can easily get an idea the project is about. So here the food is scanning with the smartphone. So by scanning the food with the smartphone, so immediately we will get the results of the food, what about the nutrition and what about the food content, what about the oil in the food. We will detect it very faster by using the smartphone. So now in this generation, we are familiar with the smartphone. So by using this technique, we can detect the food what we are going to consume. So here under global leader, rising a concern over food contaminant dim and fast. So innovating the lab and phone system, smartphone now serves a portable lab revolutionizing food safety diagnostic. And what about the compact and efficient mean? Low power and portable system for real-time results and without a bulky lab experiment. It's just a small equipment like. So coming to the working, how it going to work? Here the image which shows the smartphone based diagnostics device attached to the smartphone, likely designed for analyzing the liquid sample. Here we can observe how the liquid sample is going to be detected. So here is the LED and the diffuser and the sample lid and the sample tube. So sample tube, which is a small container holding the liquid of the food sample for the testing. So inserting into the device of the analysis. So this is the LED and this is the diffuser. The LED provides the light to illuminate the sample, which ensures the even light distribute across the sample for the accurate detection. And what about the diffuser, which ensures the even light is distributed or not? So here we can observe the control and the sample aperture. Control aperture and sample aperture. These apertures are control how the light passes throughout the sample, and they allow the specific wavelength of the light to reach the smartphone camera. And what about the lens and the camera? The additional camera helps the focus the light coming from the food sample to reach the smartphone camera, which captured the image for analysis. So finally, the smartphone serves the processing unit using this camera, captured the light interaction, focus the sample, and analyze the specialization software of interpreting the data. So here we used LFIA is a paper strip-based method for the detecting and the quantization of analysis. A liquid sample containing the analytic of interest moving under capillary action through various zones of strips on which molecule which the interacts with the analytics or the attached. So starting from one end to the another end, when the liquid is flowing from one end to another end, it is bounded by a specific antibody congested with the collated or the fluorescent. At the another end, detection in which the recognizing take place, which read out in the detections. So coming to the conclusion, in this near-far smartphone may have the ability to analyze the predict the precautions and nutrition content of the food before consuming by simply scanning the meals or whatever the food we are going to inject, could again instant insight into our nutrition profile. This innovation would empower healthier eating choices with just a quick glance at their devices. So this is my research going on, which we can scan and detect the details of the food which we are before consuming. That's thank you.
How much time it will take, madam, to detect the food?
Ma'am, it's just a few seconds that we
Just a few.
Yes, if you have a good algorithm in our smartphone, we can detect the smartphone while we are taking. So instantly we can observe the results of the food. What are
This
the
will be an app.
nutritions and what?
This will be an app in your mobile phone or an instrument you are designing?
Ma'am, it works upon the machine learning, so which we are going to research on this.
Machine learning you are using?
Yes, ma'am.
Which algorithm?
The
For
template is
efficiency.
going to ready, and just we are
Now,
working
which
on that.
algorithm in machine learning you are using?
Ma'am, algorithm in the machine learning.
Yes.
Machine
For
learning.
getting for getting the efficiency, you must using some algorithm. You trained the data set or what you did?
Yes, ma'am. Decision making framework and problem solving methodologies and research allocation and optimizing the techniques. Yes, ma'am.
It's okay.
Okay, thank you, Nandini, for your presentation. Now going to the next participant, K.
Thank
Kiran Kumar. K. Kiran Kumar, I think he is not there. Roshan Sharma. Roshan Sharma. He is also not there. Mr. Manish Kumar Tiwari. Yeah, you can share your slides and please switch on your
Okay,
camera.
okay. Oh, sharing. Yes, yes. It is visual.
Yeah, your slides are visible. Let's start your
Okay.
presentation.
So, good afternoon, everyone. I'm Satish Kola from IIT Indore, working under the supervision of Professor Parashuram Cheriesal. So, my topic is W18O49 nanofiber functionalized with graphene as a selective sensing of NO2 gas at room temperature. So, these are the outlines of the talk. So, as we all know that NO2 is a noxious gas that is primarily emitted from the motor vehicle exhaust, industrial activities, or fossil fuel combustion, etc. And its effect on us is because of the exposure to NO2 from the air that we breathe. Its toxic effect on respiratory system, cardiovascular system, on all class of people are well documented that necessitate us to follow the air quality guideline recommended by the various institutions like WHO, OSHA, NIOSH, etc. So, conventionally, WO3 is known for the research on WO3 are well documented for the detection of NO2 gas at different operating temperatures like 150, 250, and some in the form of composites are also recorded for the room temperature sensing. But if we look at the various non-stoichiometric form of tungsten dioxide, W18O49 is a very interesting material which possesses large oxygen vacancies, larger surface area, and that could be a beneficial over the WO3 in enhancing gas sensing performance. So in this work, we are choosing the W18O49 nano structure over the WO3 to test its sensing potential. So now, moreover, in recent years, we have seen that innovative strategies have been explored, like integration of the one-dimensional nanostructure with this two-dimensional carbon-based materials. So in this work, we have chosen the two-dimensional carbon-based material at a graphene state. So because of and which provides the good chemical properties like good electron transfer platform, super electron mobility, more surface active sites, and high surface area, etc. So here our objective is incorporate the one-dimensional tools with the 2D graphene chips for the enhanced gas sensing characteristics towards NO2 gas. So WO3 of photon were tied by the simple hydrothermal techniques, where moreover the graphene its composite with the graphene are also tied by the hydrothermal treatment with the different graphene weight percentage of graphene. So then the materials are characterized for the XRD characterization technique, where all the diffraction peaks in the ritual defined pattern of WO3 and WO10 of 49 are well indexed to the structure respectively. Moreover, if we look at the diffraction of the composite materials, also diffraction of the object of the low content of the graphene. Then morphology were characterized where nanofibers were obtained. This is the morphology of the pristine sample WO49 samples. Where nanofibers are with the diameter range from the 10 to 60 nanometers were obtained, and they are interlaced among them of proven like. Here, SRTM, TEM images are also provided for the best optimized samples. That is the W18049 nanofiber is composite with the graphene 1.5%. And it is observed that the W18 nanofiber are are grown on the support of the graphene sheets, which are evident from the TEM images also, and the SRTM assay indicators are also very aligned with the SRT patterns. Then aqueous were characterized to know the percentage of oxygen latent lattice oxygen or vacant oxygen chemical oxygen, where the material that is W18 and it's hybrid with the 1.5% graphene possesses lowest lattice oxygen and highest vacant oxygen and chemical oxygen. So which signifies that it could be a best it could possess best sensing potential among them. Then BT also BT surface area analysis also confirms that the sample with the 1.5 the samples that is prepared that is made hybrid with the 1.58% graphene possess highest surface area among them. So finally the materials were coated on the copper baked IDE pattern that were prepared with the DC sputtering and undergone the gas sensing test. So initially, the test is started with the IV measurement, which shows the linear behavior. That is that confirms the well formation of the contact between the material and the pattern. Then initially, the material WO3 and W18 underwent the testing test at room temperature, and it confirms that the WO3 shows non-selective detection towards all other gases, towards every gases. But W18 shows quite selective towards the NO2 gases, and it also confirms that W18 is exhibiting good sensing potential over the WO3. Then the effect of graphene content is shown here, that with the increase in graphene content from 0.5% to 1.5% to 3%, there is a decrease in baseline resistance from 1.2 ohm to 0.13 and further 97 kilo ohm. Moreover, with the increase in graphene content, there is an increase in response toward the NO2 gas also. That is, for the pristine, it is about the response is about 83. Then for the 0.5%, the response is about 94.5. Then response increases to 1. Further, even increasing the graphene content 3%, the response is decreased.
You have 1 minute left.
And more. Okay. So the sample with the graphene, the sample that is prepared with the graphene of 1.58%, so is the best response towards the NO2 gas, and it's also shows selective detection towards the NO2 gas. Moreover, the response time and recovery time is found to be quite fast, 3 seconds and 6 seconds. Yeah, the calibration test was done, which outcomes that the limit of detection is found to be less than 0 ppm. Then stability test was also performed for the longer cycle, and the tests were also performed under the relative humidity from 20% to 97%, where the device is the device that is prepared with the 1.5 graphene is found to be almost quite impressive in all forms. Then the results were also compared with the previous analysis done, and it is confirmed that which shows that our device is quite impressive in all forms at room temperature for all concentration with high response and with quite quick response and recovery time. So this is a possible mechanism that is all based on the formation of electron depletion layer where the gas adsorb and dissolve. Okay. So the finally, I will conclude that the gas sensing credit of W18 sensor or material nanofibers that is hybrid with the 1.58% graphene has proven to be a advantage in the various aspects like room temperature NO2 sensors, highly selective to NO2 gas, quite fast response time with 3 seconds and recovery time 6 seconds. Limit of detection is found to be less than 0.4 ppm. Their long device also shows long-term stability and operable in harsh environment conditions like in almost every conditions of relative humidity. So these are the references, my publications, acknowledgement. So I would like to thank my professor, IIT Indore, all my lab mates, IEEE Center, Council for organizing this symposium. So thank you for your time.
So judges, do you have any question?
No, thank you.
No question. So I request next participant, Pinky Roy, to please share her screen. I think she is not
Okay,
there.
Sumita, can I? Okay. Should I mute myself?
Yes.
Okay.
Hello,
Ashley Sunny.
I'm Ashley Sunny.
Yeah, you can share your screen and present now.
Okay. Sir, is my screen visible?
Please switch on your, yes, please switch on your camera also.
It's
Please switch on your camera also. Visible. Now you can start.
hello.
You can start now. Just share your screen and start now.
Okay. Is my screen visible, sir?
Yes.
Okay, can I start? Good evening. I'm Ashley Sunny, a research scholar working under Dr. Ramesh M. Thamangar, sir, VIT Vellore. I'm presenting on the topic low power consuming ultraviolet light assisted optical synapse using zinc oxide nanoparticles. The technology which we are using currently is based on von Neumann architecture, which the scaling is given by Hello.
Hello.
There is some issue with the sharing.
Please do the full screen mode. Your screen is not visible. Please share your screen.
Now is it visible?
Yes, it is visible. Just make it full screen.
Now it is in full screen. Is it visible?
Share the whole screen. You had just shared the slides, I think. Yeah, it is visible
So
now.
the current technology we are using is based on von Neumann architecture, and it is the scaling of von Neumann architecture is given by Moore's law, but the scaling is deviating from the ideal scaling because of the physical limitation of the bulk materials such as leakage current, scaling limits, quantum tunneling, and high power consumption. So we need an alternative architecture. There are many platforms which are being investigated, including quantum computing, spintronics, photonic computing, DNA computing, neuromorphic computing, etc. And my work is based on neuromorphic computing. For a new architecture to replace the current architecture, we have to go through 4 different stages. The first one is the fundamental science stage, where we have to find the optimal material with stability and durability and understanding the fundamental science. And second stage is the device level performance, where laboratory scale devices and architecture is investigated and find devices with low power consumption. These 2 levels we are working on. Further, it will go to the circuit level integration and a final technological products. And there are different potential material systems available, such as quantum dots, nanoparticles, nanowires, monolayer materials, and so on. I'm working on zinc oxide nanoparticles. So what is neuromorphic computing? Neuromorphic computing means brain-inspired computing. The computers we are using is digital computer, which consists of a memory unit and a processing unit. And the memory and processing unit are separated by each other. And it is called, this physical separation is called von Neumann bottleneck. But the idea of neuromorphic computer is inspired from human brain, where the memory and processing units are combined together, which can lead to a lower power consumption. So human brain consists of neurons and synapses which work together to process, and memory as memory and processing units, it consists of 10 raised to 11 neurons and 10 raised to 15 synapses. And it works in a nonlinear and complex parallel manner. Synaptic plasticity is one of the basic property of a biological synapse. It states that in a synapse, the ability of human brain to adapt the neural configuration with learning experience and environment. In biological synapse, we have a presynaptic neuron and a postsynaptic neuron connected through a synaptic cleft. When a biological spike is received in the biological first neuron, it is transmitted through neurotransmitters and a postsynaptic current is created. This can be mimicked in an artificial synapse, which is a 2 metal electrode having a insulating or semiconducting material sandwich between them. And when a artificial stimuli is applied, it will give rise to an artificial postsynaptic current. And in memory, in human brain, we can change the memory from a sensory memory to a short-term memory to a long-term memory by repeated rehearsals. This can be emulated in an artificial synapse by changing the pulse duration, frequency, intensity of the optical pulses in an optical synapse device. We have fabricated the artificial synapse using zinc oxide nanoparticles in platinum interdigitated electrodes. The nanoparticles have an average particle size of 50 nanometers, and we have used platinum electrodes having 10 micrometer gap, and a constant read voltage of 0.1 volt is applied. When the optical pulse is applied, the current will increase, and there is no instantaneous decay of the postsynaptic current. Here we have observed up to long-term memory up to 2500 seconds. And we have further characterized the synapse by applying single pulse measurements from 20 millisecond pulse width to large 12 second pulse width, and there is a linear increase in the maximum conductance. Similarly, we have applied multiple pulse measurements where 100 millisecond pulses are applied by increasing the number of pulses, and there is a increase in the maximum conductance. This is corresponding to a transition from a short-term memory to a long-term memory by increasing the single pulse width and multiple pulses. A similar increase in the maximum conductance can be observed by increasing the frequency of the pulses and varying the intensity of the optical pulse we are using, which is 375 nanometer. So we have observed a transition from... Okay, sir. short-term memory to long-term memory by increasing the pulse width, number of pulses, frequency, and intensity. And for short-term memory, paired pulse facilitation is the one of the fundamental measurements where we are applying two identical pulses by varying the pulse duration between them. And here we have obtained the paired pulse facilitation index as a double exponential decay curve with T1 76 millisecond and T2 5.36 millisecond. And we have studied the forgetting behavior by using Ebbinghaus forgetting curve, which is given by delta G max equal to exponential minus T by tau raised to beta. And here we have obtained in our measurements for a pulse of 1.5 second, beta as 0.38 and tau as 35.83. This is a fundamental measurement of decay of memory in the artificial synaptic device. And the energy consumption of the device is calculated using energy consumption equal to V into delta I, which is the increase of the current, and delta T is the pulse width, and it is calculated and it is following an exponential increase. And for a pulse width of 0.6 millisecond, we have obtained a energy consumption of 1.2 femtojoules, which is of the order of the biological synapse, which is in between 1 to 10 femtojoules. So these are the summary of my work. An optical synaptic device is fabricated using zinc oxide nanoparticles, and extended persistent photocurrent is obtained up to 2500 seconds, and synaptic characteristics are studied, and long-term memory is obtained by increasing the pulse width, number of pulses, frequency, and intensity, and a low power consumption is obtained in the device, which is of the order of 1.2 femtojoules, and Ebbinghaus forgetting curve is emulated in the optical synapse based on zinc oxide. This work is under review in applied surface science. Thank you for listening.
Yeah, okay. So, judges, do you have any questions?
Sorry? Hello?
So, I have a question. Have you calculated the non-linearity factor?
No, sir. This is the optical synaptic measurement. So it is the optical potentiation, but there is no. I have only used one particular wavelength, 375 nanometers. So when we are applying, we are getting a potentiation, but that depression is not. It is naturally happening. There is no optical pulses which can give a depression by step by step. This is optical pulse measurements. These are not electrical pulses. So there is no opposite.
Okay. Okay. So thank you. So coming on to the next participant, Roshni Oman.
Hello, sir. Am I audible?
Yes, you are audible. Kindly switch on your, just switch your slide on.
Sir, is my slides visible?
Yes, your slides are visible. Now you can start your presentation.
Okay. Good afternoon, all. The topic of my presentation is tunable memory behavior in light-stimulated artificial synapse based on zinc oxide thin film transistors. Myself, Roshni Oman. I am a research scholar with Department of EC and IT Calicut. This is an outline of my talk. Introduction. Neuromorphic computing tries to emulate the human brain functionalities using semiconductor devices working as neurons and synapses. This work reports a three-terminal optoelectronic synapse created using zinc oxide thin film transistor for application in neuromorphic computing. The persistent photoconductivity feature of the zinc oxide thin film is utilized to demonstrate the synaptic behavior. Basic synaptic functions like sensory memory, short-term memory, long-term memory, etc. have been successfully demonstrated. And extensive material characterizations have been done in order to confirm the presence of oxygen vacancies, which are a cause of this persistent photoconductivity. On to our fabrication procedure, we started with the N-type silicon dioxide wafer with an oxide thickness of 300 nanometer, subjected it to solvent cleaning. Then we went on for RF magnetron sputter deposition of zinc oxide thin film. The sputtering was carried out in the absence of oxygen and no post annealing was performed. Finally, aluminum electrodes were deposited using thermal evaporation techniques using shadow masks to form the source and drain contacts. So figure 1 shows the schematic cross section of our device. This is a thin film transistor structure. You can see the different layers. Base is the substrate, then the oxide layer, then the zinc oxide active layer, finally the aluminum contacts for electrodes. Figure 2 shows a cross-sectional FESM image displaying the various layers in a fabricated device. We carried out several material characterizations. First, to confirm that the material deposited was zinc oxide. So figure 1 shows the FESM surface image of a deposited thin film. You can see zinc oxide crystallites uniformly distributed across the thin film. Figure 2 shows the SEM energy dispersive spectra. From this you can see the elements present are oxygen and zinc with the respective concentration. Figure 3 shows the X-ray diffraction spectra. Here the dominant 002 peak at 34 degree and 103 peak at 64 degree are fingerprint for the zinc oxide material. Figure 4 is a torque plot. Torque plot is a mechanism to determine the band gap of the material. From the torque plot, we got the band gap as 3.29 electron volt, which is close to the theoretical band gap for zinc oxide, which is 3.3 electron volt. And the inset shows the absorbance versus wavelength spectrum. You can see the zinc oxide is having high absorbance till 400 nanometer, which is the UV region. I already mentioned we are utilizing the persistent photoconductivity feature of the zinc oxide material. So what is this PPC? Persistent photoconductivity means when you are giving a UV pulse, the current through the device increases. When the pulse is switched off, the current does not fall to zero, it stays at a particular value. That is called as PPC, and oxygen vacancies, which are a type of defects, are responsible for this PPC. So we carried out several characterization studies to confirm the presence of oxygen vacancies in our material. Figure 2 shows the X-ray photoelectron spectra. From this, the peak at 531 electron volt corresponds to the oxygen vacancy peak. Figure 3 shows a photoluminescence spectra. Here the weak peak from 500 to 600 nanometer corresponding to green region emission is caused by this oxygen vacancies. So TFT electrical characteristics. Here figure 1 shows the output characteristic, figure 2 shows the transfer characteristics. These were recorded in the presence and absence of UV. In both the figures you can see in presence of UV the current is more when compared to the absence of UV case, showing our device is responding well to UV light. So human memory and forgetting model, our brain upon receiving an event for the first time develops a sensory memory. When the event is coming continuously, the sensory memory gets transformed into short-term memory. When the event is coming at a high frequency, short-term memory gets transformed into long-term memory, means information is remembered for a longer period of time. So we are trying to demonstrate these basic synaptic functions through our device. So these are our results. Figure 1 shows a sensory memory. We have given a single UV pulse. The current is rising. When the pulse is switched off, the current is not instantaneously coming to zero. Figure 2 shows a short-term memory. We are giving multiple UV pulses at a low frequency of 0.1 Hz. When there are multiple pulses, current is rising. When the pulse has stopped, the current is also degrading very slowly. Figure 3 is a long-term memory. Multiple UV pulses are given, but at a high frequency of 1 Hz. Current is rising in presence of pulses. When the pulses are stopped, the current is almost staying at its constant value, showing higher retention. Figure 4 is the duration time-dependent plasticity. That is, a current through the device depend on the irradiation pulse width duration. Here two curves are shown. One for a pulse width of 10 seconds, other for 15 seconds. You can see for 15 seconds, the current is more, also the decay is less. Figure 5 is a paired pulse facilitation feature. That is, you are giving two UV pulses and current corresponding to the second pulse will be higher than current corresponding to the first pulse. If A1 and A2 are the amplitudes, PPF index is calculated as A2 by A1, and this value depends on the time interval between two pulses, delta t. So as time interval increases, the PPF index falls. Our device gives a high PPF index of 160% at the initial instant, which is pretty high compared to all the reported literatures. Figure 6 is
You have 1 minute left.
Okay, sir. Figure 6 is the light intensity dependent plasticity. That is, our current depends on the intensity. We conducted experiments for 3 UV intensities, 0.3, 0.4, and 0.6 milliwatt per centimeter square. You can see the current is highest for highest intensity. Also, the decay is least for the highest intensity cases. So on to the conclusion, our device successfully demonstrates synaptic functions like sensory memory, short-term memory, long-term memory, DTDP, PPF, etc. Our device gave a high PPF index of 160%, indicating a fast learning behavior. And we are able to obtain these good results because the sputtering was carried out in the absence of oxygen, as well as no post-deposition annealing was performed, and extensive material characterizations were performed to verify the presence of oxygen vacancies, which are the cause of this PPC. So these are my references, my publications, and thank you.
So thank you, Roshni, for the presentation. So Nikita ma'am, do you have any questions? Don't think she has any question. Can you go back to the slides having 6 images?
Sir, which slide?
I think slide number 8.
This one.
Yeah, this one.
Okay.
So here, what's the pulse width or the frequency of the light you have used?
Sir, pulse width is 1 second in all the cases. Like figure 1, 2, and 3, it is 1 second.
Okay. 1 second for a complete cycle or on off, T on, T off?
T on for one pulse width is 1 second, and off time is adjusted according to the frequency we want.
Okay. So like you have shown in figure 5, paired pulse PPF ratio, like PPF graph, and also we can see from graph 2 short-term memory that initially the current is in the range of 1.625, and after giving the second pulse it is around 1.67 microampere. Then how there is so much change in paired pulse facilitation PPF value?
Sir, actually this figure 5 PPF value, the pulse width is 1 second. Also the off time is also 1 second. So that means I have taken for frequency of 0.5 hertz.
Okay, for there you have taken 0.5 hertz.
Yeah, so short-term memory, the frequency is less. It is 0.1 hertz. So we cannot compare the value from this STM curve with the PPF curve.
Okay.
Because PPF I have taken for a frequency of 0.5 hertz.
Okay, and what's the structure of the device?
Device structure is this thin film transistor structure, as you can see in figure 1. That is, we are having a bottom substrate, then the oxide layer, then the active layer, and finally the electrodes.
Okay, as you have used aluminium as top contact for source and drain, so
Yes,
there
sir.
are possibilities that aluminium oxide might form. So how you tackle that?
Sir, aluminium?
Aluminium oxide formation at the junction, you can say, interface between drain source and ZNO thin film.
Okay. Sir, there were not such issues like these oxide formation, they were not seen to affect our synaptic responses. Anyways, we have not estimated like how much aluminum oxide is there. We haven't gone into that. We have conducted the material studies for zinc oxide film and then went on to the synaptic behavior stimulation.
Okay, thank you.
Okay, thank you, sir.
Now coming on to the next participant, Pinky Roy, are you there? Pinky Roy. Thirumaran. Thirumaran. Is also not. K. Kiran Kumar. Pinky Roy. Okay, we will. Pinky, kindly leave the meeting and again join. Pinky, are you able to hear us? Your Pinky, hello. Okay, so no other participants are there. So we will be concluding today's session, and I would like to thank Dr. Neetika Watts and Dr. Nilesh Anand Srivastava for chairing the session today. And also want to thank all the participants who participated and who joined to see the presentation. And I also request you all to please join the tomorrow's plenary talk tomorrow at 10 a.m. Okay, so thank you.
Participants can now leave the session. Thank you.